Hi and welcome to the very first lecture on Pandas and Pandas data frames. In this and the next lectures and sections, you will learn Pandas coding from scratch. But before we move to Jupyter Notebooks and start coding, first of all, I want to introduce the concept of tabular data and some terms and vocabulary that I will frequently use in this course. So in the whole course, we will work with data that is organized in a tabular manner. And in Pandas, this is a so-called Pandas data frame. So that's a data frame here with 5 famous football players, for instance, Lionel Messi and Cristiano Ronaldo. And actually each row here is one football player. For instance, we have the row Cristiano Ronaldo with some features or characteristics of this player here. For instance, we have the nationality or the club, or also the height. So the height is one column of this data frame here. And actually we can see that the height of Cristiano Ronaldo is 1.87 meters. And 1.87 is also called an element, a value or an entry of the data frame. And we can also have slices or subsets. So here we have only 2 players and only the columns nationality and club. And we can also say that tabular data or Pandas data frames are 2-dimensional, so we have 2 axes, we have rows and columns. And actually all rows and columns are labeled. And first of all, we have the so-called row index, or simply the index. And each and every element here is called an index label. So Neymar Jr. is the label of this row here. And the index shouldn't be mixed up with the columns. So the index is not the first column of the data frame, it's the index. That's the difference. And a row index can also have a name. So the row index name, in this case, it's a player, but it could also be player name or whatever. And second, we have the column index, or short columns. And the elements in the column index are called column labels or column headers. And last but not least, there's an optimal data organization in data frames, and we should always have the observations in the rows. So the observations here are the football players, and each single row should be one observation or one football player. And in the columns, we should have the characteristics, the variables or the features of the observations. So for instance, the height is a characteristic or a feature of a football player. So when working with data frames, we should always have this structure here to have the full functionality of a data frame. And the reason for this is the following. So we should make sure that we have only one data type per column. And let's have a look here if this is the case in our example. So we have the nationality column with string or text data. Then we have the club column with string or text data. Then we have the world champion column that indicates whether the player already won the world championship or not. And here we have bool or boolean values. Then next we have the height column where we have floats. So with 2 decimals, 1.70 for instance. And finally we have the column goals 218 with the number of goals that the player scored in the year 2018. And here we have integers. So in this case we have an optimal data organization, and we can be sure that we have full or maximum functionality. And in case we have mixed data types in some columns, this can restrict the functionality of the complete data frame, and this can cause severe problems. Alright, this was a short overview on tabular data and Pandas data frames. Thanks for watching, and see you in the next lecture. Bye. In this video, I will show you how to open and work with the downloaded Jupyter Notebooks and datasets. And we will also create our very first Pandas data frame. So this is probably one of the most important lectures of the whole course. And we have still the downloaded folder course materials part 1 on our desktop. And now let's go to Anaconda. So here we are on the Anaconda navigator, and we go to Jupyter Notebook. And that's the Jupyter dashboard here. And it's important to understand that this is a view on our users or home folder. So let's open our users or home folder. And here we can actually see the very same folders and elements. So for instance, Anaconda 3, contacts, desktop, documents, and so on. And also here. And if we add another element or another folder here to our users folder, then we will also see this here in our Jupyter dashboard. So this is a view on our users or home folder. And actually we know that our course materials part 1 folder is on our desktop. And therefore we click here on desktop. And this is a view on our desktop. And here we can see the unzipped folder course materials part 1. And let's click on it. And now let's go to video lecture notebooks. And here we can actually see all notebooks and also all data sets that we will use in part 1 of this course. And actually we could simply open the very first notebook, Pandas Basics. So that's the section here. And here we can see the complete code that we will create in the next lectures. But now let's create a new Jupyter notebook and let's try to start from scratch. So we go to New and we select the Python 3 notebook. And actually we should title or name our notebook. So for instance, Pandas 1. And let's click on rename. So we have created now the Jupyter Notebook Pandas 1. And if we go now to our Jupyter dashboard, here to our overview, then here we can see that we have successfully created Pandas 1 Jupyter Notebook. And as this is actually a view on the folder Course Materials Part 1, then we should also see this new Jupyter Notebook also in the folder here. So let's double check this. Let's go to Video Lecture Notebooks. And here we can see the new Jupyter Notebook Pandas 1. So again, this is a view on the folder. And now the plan is to import the Titanic dataset that is stored in the CSV file titanic.csv into our Pandas 1 Jupyter Notebook. And it's important to see and understand here that both files are in the very same folder. So we have the Jupyter Notebook Pandas 1 and the CSV file titanic.csv. So they are located in the very same folder. And therefore the import is pretty straightforward. So now let's go back to Pandas 1. And let's create some more cells with the B key. And first of all, we have to import the Pandas library. And we should always import pandas with the code import pandas spd. So PD is the abbreviation for pandas, and it's the convention to import pandas spd. So everybody knows that PD stands for pandas. And now we can import the Titanic dataset from the CSV file titanic.csv. And there's actually the pandas method pandas pd read CSV, and then we have to pass the file name within the parentheses, and actually as a string in quotation marks. So let's again have a look here. So the file name is the titanic.csv. And now let's run the cell. And this looks like a data frame. So here we have 891 rows and 9 columns. And finally, we can also store the data frame in memory and assign it to a variable. And let's select the variable Titanic. And let's run the cell. So we have successfully saved the data frame in the variable. And let's simply print our data frame again. So here we have the data frame. And we can see that we have actually 891 rows and 9 columns, but by default we can only see the first 5 rows and the last 5 rows. And I will show you in the next lecture how to change the display options here. But now let me show you the most frequently made mistake when importing CSV files into Pandas. And let's go back to our desktop. And here you can see the CSV file iris flowers, so short iris, and the name is iris.csv. And obviously this CSV file is not in the course materials folder, it's just located on our desktop. And now let's try to import the iris flowers dataset into our Pandas 1 Jupyter notebook. So let's copy here the code and let's paste it. And actually the file name is iris.csv. And here we get a file not found error. And it says here that the file iris.csv does not exist. Well, it actually does exist, but on our desktop. However, we can only import a CSV file if the CSV file and the Jupyter notebook where we are coding in are located in the very same folder. And now let's go back to our Jupyter dashboard. So here we have the folder video lecture notebooks. That's the subfolder, and the main folder is course materials part 1. And actually we were able to import the CSV file titanic.csv to Pandas 1 because both files are located in the very same folder. And now we tried to import the iris.csv file into Pandas 1, and this does not work because they are not located in the very same folder. So here we do not have the iris flower CSV file. And therefore we get the file not found error message. So now what can we do if we want to import the iris.csv file into Pandas 1? Then actually there are two solutions. So either we can simply drag and drop here iris into the video lecture notebooks folder where we have Pandas 1. So that's the hands-on approach. Or let me show you a better approach. Or we can also upload here in the Jupyter dashboard, and let's click here on upload. And let's select the desktop. And here we can see the iris.csv file, and let's click on it. And here we have now the option to upload the CSV file into this folder here. So we have done this, and we can actually now see iris.csv. And now let's go back to our Pandas 1 Jupyter notebook. And let's again try to import the iris.csv file. And now it works. And again, the reason is pretty simple. So the Jupyter notebook Pandas 1 and the CSV file are located in the very same folder. And if they are not located in the very same folder, we get a file not found error. However, there's an alternative way how to import a CSV file, even if the file is not located in the very same folder. But this is more complicated, and you can drop me a message and ask for the alternative way. But actually, I do not recommend the alternative way. All right. So as a final remark, if you get a file not found error, and if you do not know why and what to do then the best advice is to rewatch this video. All right, thanks for watching, and see you in the next lecture. Bye. Hi and welcome back. We have still imported the Titanic dataset, and we have saved the data frame in the variable Titanic. And we've already seen that we can simply print or output the data frame by running the cell with the variable Titanic. So here we can see the data frame, or at least the first 5 rows and the last 5 rows. And you might know that there's a second way how to print things in Python. It's with the print function. And let's pass Titanic. And now let's run the cell here. And actually the data is of course the very same, but the style isn't as nice as we had before here. And by default, Jupyter notebooks nicely display Pandas data frames in an easy to read HTML table if the data frame variable, so in this example Titanic, is in the last line of a cell, and if we simply run the cell. However, if we use the print function here, then the data frame is rendered in a less readable, poorly formatted text-based output. So there's actually no reason why we should print or display a Pandas data frame with the print function. So that's actually the best solution here. Now we still have the problem that by default we can only see the first 5 rows and the last 5 rows. And the reason is that there are some standard or default display settings. And let's have a look here. So we have pd.options.display. And the first setting is the max row setting. And the default setting is here actually 60. And there's also a second display option or display setting. And it's actually the min row setting. And the default value is here 10. Now the rule how Pandas displays the data frames and the rows is pretty simple. So if the data frame has equal or less rows than the max row setting, so by default it's 60. So if the data frame has less than 60 rows, then by default Pandas shows all rows. But if the data frame has more rows than the max row setting, so by default more than 60 rows, and typically our data sets have more than 60 rows or more than 60 observations. And in all these cases, then the min row settings prevail. So by default, we see in total 10 rows. And that's actually the first 5 rows and the last 5 rows. Now, what if we want to change this? And let's assume that we want to see the first 10 rows and the last 10 rows. So in total 20 rows. Then we can simply set the min row setting to 20. And let's run the cell. And let's again print Titanic. So let's do this here in a new cell. And then we can see that we have the first 10 rows and the last 10 rows. So in total 20 rows. And actually we could also print or output all rows of a data frame. So of course this doesn't make sense if the data frame has thousands or even millions of rows. But in our example here with 891 rows, this is still feasible and could make sense. And the only thing we have to do is actually we have to set max rows to a number that is equal or higher than the total number of rows in our data frame. So in our case, at least 891. And let's again print Titanic. And here we can now scroll down. And we could actually analyze and observe all 891 rows of our data frame. All right. And actually at this point, it's important to mention that the display settings changed in Pandas version 0.25. So they actually introduced the min row setting. So before we only had the max row setting with the default value 60, and there was no min row setting. So min rows was actually none. So that was actually the setting in Pandas version 0.24 and earlier. And the default behavior was when printing the data frame with more than 60 rows, then by default Pandas showed the first 30 rows and the last 30 rows. So in total 60 rows. And this is just for you to know, as you might see this behavior in other courses or other videos, and also in some videos of this course that are based on Pandas version 0.24. So just for you to know here. And now let's come to the very helpful methods head and tail. And first of all, let's focus on the head method. So we have here Titanic.head. And by default, the head method shows the first 5 rows of a data frame, but we can change this. So if you want to see the first 10 rows, then we can simply pass here 10, or the first 20 rows. And second, there's the tail method. And by default, we can see here the last 5 rows. But of course, we can also get the last 10 rows by passing 10. So the default argument is actually here 5. But we can change this to 10 or also to 2 to see the last 2 rows. And now we're actually best equipped to make a very first inspection of our data frame. So we can change display options, and we can inspect the first 5 rows or the last 5 rows or all rows or the first 30 rows or whatever. And actually we will do the very first inspection in the next video. So hope to see you there. Bye. Alright, after having imported the data, we are coming now to the next and one of the most important steps when working with data, the very first inspection. And typically when working with data and with new data sets, we don't know much about the data, and before we can start with our primary task, and this can be explanatory data analysis, data visualization, statistical analysis, machine learning, or whatever. So before we can start with this, we need to perform a very first inspection, and based on that first inspection, we can plan the next steps. For instance, we could come to the conclusion that we need additional data, or that we need to clean the data, or transform the data, or handle missing values, or whatever. And it is very often the case that this first inspection is underestimated. However, coming from the business side, I have to emphasize that understanding your data and understanding your task is the key to success. So we have still imported the Titanic dataset, and we have saved it in the variable Titanic. And here we can see the first 5 rows and the last 5 rows, and also the column headers or column labels. And in the vast majority of cases, this is already sufficient to get a very first impression. So here we can see we have 891 rows and actually 891 observations, and each and every observation or each row is here one passenger on board of the Titanic, and we have 9 columns. And each column is actually a characteristic or a feature of the particular passenger. So here on the left side, we can see the index of our data frame, and the default index is actually a range index. And a range index simply consecutively numbers the rows. So starting with 0, 1, 2, 3 and until 890. And typically when importing data from a CSV file, by default we can see here a range index. And now let's come to the columns. So first of all, we have the survived column. And this indicates whether the passenger survived the disaster or not. And actually 0 stands for the passenger did not survive, and 1 stands for survived. Then we have the passenger class. So in total we had 3 passenger classes, so 1, 2, and 3. And the 1 was of course the first class. Next we have the gender or the sex of the passenger, so we have of course males and females. Then we have the age in years, so for instance here 22. Then next we have the column SIP-SP, and this stands for siblings and spouses. And this is actually for each and every passenger the number of siblings and the spouses of this passenger on board of the Titanic. Then we have PARCH, which stands for parents and children, and this indicates the number of parents and children of that particular passenger that were also on board of the Titanic. So the very first passenger here was a 22-year-old male passenger in the 3rd class, and he obviously did not survive the disaster. And he also had probably his wife on board. Then next we have the fare or the ticket price. And I don't know if this is in dollar or in British pound, but this passenger paid $7.25 or pound for the ticket. Then next we have the port of embarkation. And for instance, S stands for Southampton. And last but not least, we have the deck where the cabin of the passenger was located. And for instance, here we have the C deck or the B deck. And we can also see some values called NaN. And this stands for not a number. And this indicates missing values. So for instance, for this passenger here, we simply do not know the age. And typically when working with real-world data, missing values are very common. And actually Pandas is designed to work with and handle missing values. So this is a very important concept, and we will go into much more detail later in this course. Next, there's one very important method for data inspection. It's the info method. So let's run the cell here. And the info method is actually one of the most important methods in Pandas, as it summarizes the data frame and shows important meta information at a glance. So let's have a look at the output here. And first of all, we can see the data type or the class that the object that is stored in Titanic belongs to. And it's obviously a Pandas data frame. Next, we can get some information on the index. And we've already seen that here we have a range index with 891 entries from 0 to 890. And then we get an overview on the columns. So we have 9 columns. And these columns here are consecutively numbered from 0 till 8. And first of all, here we have the column label. Then we have the non-null count, which gives us actually the number of non-missing values. So in total, we have 891 entries, and obviously in the survived column and in the P-class column and the sex column, we have no missing values. So we have 891 non-null or non-missing values. But here in the H column, we can see that we have 177 missing values. And also in the embarked column, we have 2 missing values. And we have over 600 missing values in the deck column. Finally, we have also some information on the data type in the columns. And it's actually no surprise that in the survived and P-class column, we have integer. Then in the sex column, we have a so-called object data type. And actually, this stands either for string or text data, or also for mixed data types. So whenever we have object, it's not 100% clear whether we have string or text data, but this is pretty likely. Then next in the H column, we have float data. So here we have 1 decimal, 35.0 for instance. Then in the zip-sp and in the parch columns, we have integers. So we have actually 0 parents or 2 parents and children and so on. And finally in the embark column and deck column, this is also here an indication that we have string or text data. So this makes sense. Here we have S, C, C, B, and so on. And finally, we get here a summary of the data types. So we have 2 columns with floats, 4 columns with integers, and 3 columns with the data type object. And last but not least, we also have the memory usage. So this is a very small data set with 62.8 kilobyte. But of course, we could also have data frames or data sets with megabytes or even gigabytes. So again, the info method is really useful and helpful. And actually, the functionality and the behavior of a data frame is determined by only few things. It's the index. So a range index behaves different than a datetime index with datetime information. And second, we have the columns and the data types in the columns. And last but not least, also the missing values. So these factors actually determine the functionality of our data frame. And we can see those factors at a glance by calling the info method. So as a summary, before and also while you're working with your data and your data frame, you should regularly check your data frame with the info method. And to draw an analogy, when you go by car, you regularly check fuel, oil, and speed to reach your destination safely. And that's exactly the same with data frames and the info method. All right. And finally, let's have a look at the very helpful method to describe. And by default, the describe method returns some summary statistics on numerical columns. So here we have the numerical columns survived, P class, H, and so on. And first of all, we have here count. So this is the number of non-missing values. Then we have the mean value. And the mean value in the survived column actually stands for the survival rate. So in total, 38% of all passengers survived the disaster, as we have 1 for survived and 0 for not survived. Then we have the standard deviation of the values and also the minimum. So the youngest passenger on board was, for example, 0.42 years, and actually that's a baby. Then we have the 25th percentile, the 50th percentile, which is actually also the median. And that means that, for instance, 50% of all passengers were younger than 28 and 50% were older than 28 years. And also we have the 75th percentile and finally also the maximum values. So the highest fare or the highest ticket price was 512. And actually with the describe method, we can also analyze the non-numerical data. So let's copy here. And let's paste. And then we can use the include parameter. And here we can pass capital O. And by doing so, we actually select all columns where the data type is object. And typically these are non-numerical columns with text data. So let's run the cell here. And here we have a summary for the sex, embarked, and deck column. So count also stands for the number of non-missing values. Then unique actually indicates the number of unique values. So in the sex column, we only have male and female. Then next we have the most frequent value, and this is here in the sex column male, and the frequency is 577. Alright, this was the very first inspection of our data, and by simply inspecting the data and by running 2 or 3 methods here, we already know quite a lot about the data, and this helps for our further analysis. So thanks for watching, and see you also in the next video. Bye. This lecture is a short excursus to object-oriented programming, and in Python everything is an object, and of course also our data frame that is stored in the variable Titanic is an object. And we can actually check the data type of an object with the Python built-in function type. So let's create a new cell here. And let's pass Titanic to the function type. And let's run the cell here. And here we can see the data type pandas data frame. Or we could also say that the object is an instance of the class pandas data frame. And actually in Python, the functionality of an object depends on attributes and methods that are defined for the class the object belongs to. And actually the pandas data frame has dozens of methods. And over 1,000 developers have worked for years on it to create and improve the functionality of pandas. And as a result, pandas is and will be the most powerful data handling and data analysis tool in Python. Before we're coming to attributes and methods, let's go on with some more Python built-in functions. And typically we can pass all kinds of objects to Python built-in functions. And depending on the class the object belongs to, a Python built-in function for that particular class is defined or not. So let's have a look at some more examples, and let's create some more cells here. And first of all, we have the length function. And you might recall that with the length function, we can determine the number of elements in a list or also in a string object. And let's simply try to pass our Titanic data frame to the length function. And here we get 891. So obviously the length function returns the number of rows in our data frame. Next, we can also try to use the around function. So we pass Titanic. And then let's assume that we want to round to 0 decimals or 0 digits. And let's have a look here. And obviously we have rounded all elements in numerical columns to 0 digits or decimals. So for instance here in the age column and in the fare column. Next, we can also try to convert the Titanic data frame to integer by passing Titanic to the int function. So I don't know how this should work, and let's have a look if this is defined. And obviously this is not defined. So the argument for the int function must be a string or a number and not a data frame. So this is not defined. And finally, we can also try to pass Titanic to the min function. So you might recall that the min function determines the minimum element in a list, for instance. And let's have a look here. And this is actually a surprise. Here we get H. And the explanation is that we get the minimum column label. And actually we get the minimum from an alphabetical point of view. So H actually starts with an A here. And actually one might have expected that we get the minimum H or the minimum var, but we simply got here the minimum column label. So the functionality of Python built-in functions is of course limited, and that's the reason why we have methods and also attributes that are specifically created for Pandas data frames. And first of all, let's come to some attributes, and let's create some cells here. An attribute is a feature or characteristic of an object that is already stored in the object. And let's have a look at some characteristics of the Pandas data frame. So first of all, let's get the attribute shape. And we can actually get the attribute with the dot notation. And here we have shape. And this is actually nothing new. So here we have the shape of our data frame with 891 rows and 9 columns. Then next, let's get another attribute. It's actually the size attribute. And here we get actually all elements in our data frame. So that's actually the number of rows multiplied with the number of columns, 891 times 9. Next, there's also the index attribute. And here we get actually the index of our data frame. So here we can see that this is a range index from 0 till 891 with step 1. And finally, we can also get some information on the columns. So there's also the attribute columns. And here we get actually the column labels, so survived, p-class, sex, age, and so on. Now let's go on with some data frame methods, and let's create some cells here. So a method is like a function, but specifically designed for that data type or class. And actually functions and methods are also callables. And like in a function, we can define method parameters inside the parentheses to customize the method. So we have already seen some data frame methods. And first of all, we have the head method. And by default, the head method outputs the first 5 rows. But we can customize the behavior of the head method with the parameter n. And here we can define the number of rows, so we can set this also to 2, for example. Next, we've already seen the info method. So this is a very important method. And finally, another example is the min method. And before we have seen that the min function didn't return the minimum value in the var column or age column. And let's have a look what the min method returns here. And it actually returns the minimum value in each column. So the minimum value in the survived column is 0 in p-class 1. Then alphabetically a female in the sex column. Then we have the youngest passenger. And we have the value 0 for SIP-SP, parch, and also fare. So there are obviously some passengers who didn't pay anything for their ticket. Finally, let's come to a very powerful concept, not only in Pandas, but also in other libraries and other object-oriented programming languages. It's method chaining. And let's have a simple example here. So first of all, let's try to calculate the mean value in all columns. And we can actually do this with the mean method. So here we have the mean values in all columns, and for instance, the survival rate is 38.3%. And now we can also sort those values from high to low or from low to high. And we can simply chain another method. It's the sort values method. And let's call the method. And by default, the sort values method sorts here all elements from low to high. So we're starting with the lowest mean in the parents and children column until the highest mean value in the fair column. And finally, we can also only have a look at the first two elements. And it's no surprise that we can chain here the head method. And we can pass 2 to get the first two elements. And again, this concept is called method chaining, as we chain the methods one after another. And of course, we will see a lot more examples of method chaining in the next lectures and sections. And finally, let's go to the Pandas webpage, to Pandas data frame. And here we can see a list with all attributes. So that's the attributes here for Pandas data frames, and also all methods. And here we have quite a long list. So in our course here, we will cover many of these methods. So thanks for watching, and see you in the next lectures. Bye. We are coming now to one of the most frequently used operations in Pandas, selecting one or many columns. And we have still imported and saved the Titanic dataset. And you might recall from sequences like lists, strings, or NumPy arrays that we can index these objects and select certain elements with the square brackets index operator. So let's try this out here. And then we can open square brackets. And actually, to select one column, we can simply pass the column label as a string, so within quotation marks. And let's assume that you want to select the H column. Then we can simply code here H. And now let's run the cell here. And here we have only the H column, the first 5 elements and also the last 5 elements. And on the left-hand side, we can still see the range index. And actually, the output here is a so-called Pandas series. So actually, the Pandas library has some data types. So we already know the Pandas data frame. And this is here a Pandas series. And we could say that a Pandas series is very similar to a data frame, but a series only shows one column or one row. So to say, it's a one-dimensional labeled array, and it's called labeled because still we have here the index. So the values in the H column here are still labeled with the index labels. And later in the course, we will have a closer look on Pandas series, but for the time being, you should simply notice that this is here a Pandas series. And the name of the series is actually the former column label H. And here we can see that in total we have 891 elements, and the data type is float. And we can also check the data type with the type function. So let's go here to command mode, and let's copy and paste with C and V. And let's use here the type function. And no surprise, this is a Pandas series. So now we have selected one column, but now let's assume that we want to select 2 or many columns. And again, let's copy here and let's paste. Now let's assume that we want to select the H column and also the sex column. Then let's try the following. So let's pass here H and sex. And here we get an error message. And it says here key error, so there's no column label that consists actually of a tuple with H and sex. But of course, there's a workaround for this. So let's again paste here the code. And actually, if we want to get 2 or many columns, then we have to pass the column labels as a list. So we have to create here a list and actually pass age and sex as 2 elements of the list. And now let's also close the list here, and let's again run the cell. And here we get now the 2 columns, age and sex. And obviously, if we select 2 or many columns, then the output is again a pandas data frame. And we can also check this here. So this is a pandas data frame. Now let's again copy and paste the code. And actually we have coded age and sex, and therefore the sequence is here age and sex, but we can also change the sequence. So first of all we have sex, and then we have age. And by doing so we can also change the output. So let's have a look here. And now we have the sequence sex and age. And finally we can also select multiple columns. So let's copy and paste. And for instance, we can also select the fair column. So we code comma and fair. And here we have now the 3 columns. And actually before we have seen that if we select only 1 column, then the output by default is a panda series. But if we pass only 1 column also within a list, so let's try this out here. And now let's create a list with only 1 element, so the age. Then here we get obviously a pandas data frame, and we can also check this here. So when selecting only 1 column, you might ask yourself whether it's beneficial to have a series or a data frame. And we will see later in the course, in the vast majority of cases, it doesn't matter, as series and data frames share most of the methods. So there are only very few methods that only work for data frames, and there are very few methods that we can only use on series. But generally speaking, most of the methods are available for both types. Alright, thanks for watching, and see you also in the next lecture. Bye. Hi and welcome back. There's also a second alternative to select 1 column, and we can use the dot notation or attribute notation. And we have still imported the Titanic data frame or data set. And a data frame with the column age has also an attribute dot age. And let's run the cell. And here we can see the age column, and also here this is a pandas series with 891 elements. So when selecting 1 column, the dot notation and the square brackets notation are equivalent and lead to the same output. And we can also check this with the equals method. So let's have a look inside here with Shift tab. And the equals method tests whether 2 objects contain the same elements. And let's copy here our code where we selected the age column with the square brackets notation. And let's paste it here inside the method equals. And now let's run the cell. And here we can see that we get a true, so both alternatives lead to the very same result, the age column. And there's actually some controversy which alternative to prefer. And some people argue that we shouldn't use the dot notation, as it can lead to errors in some cases where we have unclean data. For instance, the dot notation does not work in case the column label contains white spaces. And actually I don't agree with that, because we should avoid to work with unclean data anyway, and we should clean the data before we start with our primary tasks. So I use both alternatives, but I'm pretty lazy and I prefer the dot notation as it is less to code. So for instance, to get the embarked column, I simply use the tab completion twice, and that's it. So I start with Titanic, then I use tab and enter, dot, and then I start with emp, and also here I use the autocomplete, and that's it. Alright, thanks for watching, and see you also in the next lecture. Bye. In the next 2 lectures, you will learn how to select the rows, columns, and elements of a data frame by their positions, and this is called position-based indexing. For instance, you will learn how to select the second row or the last row, or the first 2 columns of a data frame, or even more complicated, the element that is located in the 7th row and 3rd column. But before I want to recap 2 fundamental concepts that are valid not only for Pandas, but for Python in general and also for other programming languages. It's zero-based indexing and negative indexing. And you might recall from sequences like lists, strings, or NumPy arrays that the very first element is at index position 0, then the second element is at index position 1, and so on. So we start with the position 0. And that's the reason why it's called zero-based indexing. So zero-based indexing also applies for Pandas data frames, and the only difference is that a data frame is 2-dimensional, so we have rows and columns, and therefore we have index positions for rows and also for columns that follow the zero-based indexing concept. So first of all, let's focus on the column index positions, and just to recap here, so player here is not a column but the index, and therefore the very first column is nationality at index position 0. Then we have club at index position 1, and so on. And the same applies also for the row index. So we have the very first row, Lionel Messi, and this row is at row index position 0. Then we have Cristiano Ronaldo at index position 1, and so on. So this is zero-based indexing, but there's also a second concept, and it's called negative indexing, and this can be applied as well. So we can either use zero-based indexing or negative indexing, and it depends on the specific case which one makes more sense. And now let's have a look. So negative indexing means that the very last column is at index position -1, that's the goals to 18 column. Then the second last column is at index position -2, and so on. So finally, the very first column, nationality, is at index position -5. And of course, this also applies for the row index. So the very last row, Manuel Neuer, has the index position -1, and then we have -2, -3, and so on. And actually, for your convenience, you can find this slide for download in the attachment of this lecture. Alright, thanks for watching, and see you in the next video. Bye. In this lecture, we will perform position-based indexing with iLoc. But before we start, let me introduce a new dataset that I will frequently use in our course. It's the Summer Olympic Games dataset, containing all medals that were awarded in Summer Olympic Games from 1896 until 2012. And first of all, let's import Pandas. And then we import the Summer Olympic Games dataset from the CSV file summer.csv. So in our download materials in our folder here, we have also the CSV file summer.csv. And we save the resulting data frame in the variable summer. And let's have a look at summer, a very first quick inspection. So we have in total over 31,000 rows and 9 columns. And actually each and every row is one medal that was awarded to an athlete. And for instance, let's have a look at the very first row. So we have the athlete Alfred Hayos from Hungary. He's a man. And he won the gold medal in the edition 1896 in Athens in actually the event 100-meter freestyle. And this is a swimming discipline or event, and the sport is aquatics. And let's inspect also the very last row. And here we have Jimmy Lidberg from Sweden, and he won the bronze medal in the event Freestyle Wrestling until 96 kilograms in the edition 2012 in London. Now let's also call the info method. And here we can see that we have a range index with over 31,000 entries. And actually we have 9 columns. And we only have very few missing values in the country column. And actually we have only one numerical column. So we have the data type integer in the year column. And in all other columns we have text data and actually strings. And this is indicated by the data type object. And finally, we can also see that we have a memory usage of 2.1 megabyte. So this is a larger dataset than the Titanic dataset, but still it's a pretty small dataset. And again, by default, we can see that we have a range index, but actually we can also change this. And we can set each and every column of our data frame as being the index. And we can determine this already when we import the CSV file. And there's the parameter index col. And here we can pass the column label for the column that we want to have as index. And here in our case, it could make sense to have the athlete column with the athlete names as the index. So let's pass here as a string athlete. And now let's run the cell again. And let's have a look at our data frame. And now here on the left-hand side, we have the new index athlete with all of the athlete names. And we can also rerun the info method. And here we can see that our index changes from a range index to an index with over 31,000 entries from Alfred Hayos until Jimmy Lidberg. And now let's start with position-based indexing. And let's assume that we want to get the very first row. So the row with Alfred Hayos. And let me show you the code. So we start with summer. And then we have to use the ilog operator. So whenever we want to perform position-based indexing, we have to use ilog. And then we have to open square brackets. And then we have to pass the position of the row that we want to get. And in our case here, it's the very first row at index position 0. So 0-based indexing applies also here. And let's run the cell. And here we can see the very first row. And the same as with columns, if we only get one column or one row, then by default the result is a Pandas series. So here we have the values of the very first row. So for instance, 1896 are Athens and aquatics. So that's the values in the columns here. And actually as the name of our Pandas series, we have the index label Alfred Hayos. So as a summary, our Pandas series here consists of the values taken from the very first row. And we also have an index here, and these are actually the values that we had before as column labels. So here city sport, and these labels are now the index labels in our Pandas series. And for the sake of completeness, we can also check the data type. So it should be a Pandas series. And that's true. And now let's go on with a second example, and let's assume that we want to get the second row. It's Otto Herschmann at index position 1. And then we can simply pass 1 to the ilog operator. And then we get the second row with the values. And the name of the Pandas series is Otto Herschmann, which was the former row label. So these were two examples of zero-based indexing, and now let's come to negative indexing. And let's assume that we want to get the very last row. So here Jimmy Lidberg at index position -1. Then the code is pretty straightforward. And here we have to simply pass the index position -1. And then we get the row with the values for Jimmy Lidberg. All right. Next, let's assume that we want to get the rows at index positions 1, 2, and 3. So these are those 3 rows: Otto Herschmann, Dimitrios Drivas, and Ioannis Malokinis. And we simply have to pass a list with the index positions. So that's one solution. So we open here a list with additional square brackets, and then we have the index positions 1, 2, and 3. And of course we get here Otto Herschmann, Dimitrios Drivas, and Ioannis Malokinis. But there's also a better solution for this, and instead of passing all positions explicitly, we can also actually slice here our data frame. So let's remove the list here. And actually we want to get the rows from index position 1. So this is inclusive. And actually we can code the following. So we want to have 1 until, and for until we can code a colon. And if we pass now index position 3, then we only get 2 rows. So the rule in position-based indexing is that we slice from position 1 inclusive until position 3 exclusive. And therefore, if you want to have positions 1, 2, and 3, then we have to slice from 1 until 4 exclusive. And here we have those 3 athletes. Now let's assume that we want to get the first 5 rows. And there are actually 2 options. So either we can explicitly code from index position 0 until index position 5 exclusive. So this works. Or even more efficient, if we start from the very first row, we can simply code colon 5. So the first 5 rows. Next, let's assume that we want to get the last 5 rows. And this works pretty much in the same way. So we can code from index position -5 until the very last index position. And actually it's important to understand that the very last row is here inclusive. And it would be wrong to code the very last row explicitly. So this gives from index position -5 until index position -1 exclusive. So here we have lost Jimmy Littberg, and therefore the last 5 rows is simply -5 colon. All right. Finally, we can also get all rows. So this is a no-brainer, but we could do the following. So from the very first row until the very last row inclusive. And here we get all rows, so over 31,000 rows. And finally, we can also perform some more advanced operations. So for instance, we can pass a list with index positions that are not neighbors actually. So for instance, 2, 45, and 5,467. So this also works. And this was a short introduction to position-based indexing with iLoc. And in the next video, I will show you how to select rows and columns, and also single and multiple elements with iLoc. So see you there. Bye. All right, we are continuing with position-based indexing with iLoc, and we have still imported and saved our Summer Olympic Games dataset in the variable summer. And let's get the first 10 rows here. And now let's assume that we want to select one single element of our data frame, for instance, the element Hungary. So Alfred Hajos is from Hungary. And actually the element is in the very first row at index position 0. And in the column with index position 0, 1, 2, 3, 4. And getting this element is pretty straightforward with iLoc. So we code the following: summer.iLoc, and then we open the square brackets. And we already know that we can get the very first row with 0 here. So that's the first row. But we are only interested in the value in the column at index position 4. And therefore we code the following. So we introduce here a comma, and then we have 4. And actually the rule is pretty simple. So on the left hand side of the comma, we can determine the rows or the index positions of the rows. And on the right hand side of the comma, we can determine the columns or the index positions of the columns. So in our example, it's one row at index position 0 and one column at index position 4. And let's run the code here. And here we get Hungary. And actually that's the real power of the ilog operator. So we can, in only one operation, we can index and slice for rows and columns. And of course we can also perform some more complex operations. And let's assume that still we are interested in the very first row, but now we want to get the values in the first 3 columns. Therefore we can code the following. So on the left hand side of the comma, we have the row at index position 0. And on the right hand side, we want to have the first 3 columns. So colon 3. And this gives us here a Pandas series with these 3 elements. And of course, instead of having here a slice, we can also perform more complicated operations. So let's assume that we are still interested in the very first row at index position 0, but we want to have the values in the columns at index positions 0, 2, 5, and 7. And of course, this also works here. And finally, let me show you an even more complicated example. So of course, also on the left-hand side of the comma, we can make it more complicated. And we could slice from the row at index position 34 inclusive until row at index position 39 exclusive. So this is no problem. And last but not least, we can also select complete columns with ilog, and that's pretty straightforward. So let's assume that we want to get the country column at index position 4. And we simply have to code here on the left-hand side of the comma that we want to get all rows. And that's here the country column with over 31,000 elements. And actually before we have also seen 2 other alternatives how to select entire columns. So either with the dot notation or with square brackets. And let's simply make sure that these 3 alternatives deliver the same output. And we can check this with the equals method again. And then we can pass here summer.country. And let's run the cell. And here we get a true. And for the sake of completeness, the third alternative is the square brackets alternative. And this actually gives us, of course, the same output. Alright, thanks for watching, and see you also in the next lectures. Bye. This and the next videos are about label-based indexing and slicing with the log operator. And in a minute you will see the limitations of position-based indexing and why we also need label-based indexing. And you will understand the difference between position-based and label-based indexing. And we have still imported our summer data frame. And let's assume that we want to get the third row at index position 2 with Dimitrios Drivas. Then we have already learned that we can do this with the ilog operator and pass the row index position 2. And this works pretty well. So here we have Dimitrios Drivas. However, our task is typically a bit different. So we actually don't know the index position of a row. And we simply want to get the row or the medal of Dimitrios Drivas. In this example here, it's obvious, so we can simply count the 0, 1, 2. But there might be more complicated or less obvious cases. And therefore, there's also the option to select this row with label-based indexing by passing the label of the row Dimitrios Drivas. And this works pretty much in the same way as position-based indexing, But now with label-based indexing, we have to use the log operator. So let's do this here. We have summer.log, and also here we have square brackets. And then we have to simply pass as a string, so within quotation marks, the row label Dimitrios Rivas. So let's copy here. And let's paste and let's run the cell. And of course, here we get the very same output, so the row with Dimitrios Rivas. Next, let's come to a more real-world example. And let's assume that we want to get all rows with Michael Phelps. So Michael Phelps was a very successful athlete in swimming, actually. And let's try to get the rows. And we can simply replace Dimitrios Rivas with Michael Phelps. And we actually apply the very same format. So we have the surname with only capital letters. So we have here Phelps. And the first name is Michael. And now let's run the cell. And here we get multiple rows. So we have multiple entries of Michael Phelps. And that means that he actually won many medals in the Summer Olympic Games, starting in the year 2004 and ending here in 2012. So when we perform label-based indexing, then we got all occurrences of the particular label, in this example, Michael Phelps. And with this, we have actually reached the end of this video, and we will continue in the next lecture. Bye. In the last lecture, we have seen that our index contains duplicates like Michael Phelps. This is allowed in Pandas, and actually a data frame index should not be mixed up with a primary key in relational databases. So a primary key in databases must contain unique values and uniquely specifies a row. So each and every row can clearly be identified by the primary key. And in Pandas, there's no obligation to have unique values in the index. And the question is now, should we have a clear identifier? And the answer is probably yes, that's the best practice. However, Pandas gives us the flexibility to have an index with duplicates. And in some cases, it is totally fine to work with that as long as you know the pitfalls and limitations of a non-unique index. And in this and the next lecture, we will see some of these pitfalls. And actually, to summarize, in case you have any doubts, you are definitely on the safe side when you simply use a range index, because a range index is unique. Alright, now let's go on, and similar to position-based indexing with ilog, also label-based indexing with log allows to simultaneously index and slice for rows and columns. So let's assume that we are interested in all medals that Michael Phelps won, but actually we are only interested in the column medal. Then we can actually do this. So let's copy and paste. And also here with the log operator, we can introduce a comma. And on the left-hand side of the comma, we can define the row labels. And on the right-hand side, the column labels. And in this case, we want to have all rows with Michael Phelps and the column medal. So let's run the cell. And here we get only the column medal for all rows where we have Michael Phelps. Alright, now let's copy and paste the code. And of course, you can also get more than only one column. And let's assume that you want to get the columns medal and event. Then we can simply pass here on the right-hand side of a comma a list with the column labels. So let's open here a list. And for instance, let's also select the column event. And here we have now the medal and also the event for all medals that Michael Phelps won. Alright, now let's copy and paste. And of course, also on the left-hand side, we can have more complexity. And let's assume that you want to have medal and events for all medals that either Michael Phelps or Carl Lewis won. Then we can also pass a list here on the left-hand side. So we add here Carl Lewis. And let's again run the cell here. And here we have, first of all, Michael Phelps, and finally also all medals of Carl Lewis. Last but not least, we can also select complete columns with the log operator. And let's copy and paste. And let's assume that you want to have all rows for the columns medal and event. Then here we can simply pass a colon for all rows. And this works as well. Now let's go on and let's have a look at the first 10 rows with the head method. And so far we simply passed row and column labels in a list to the log operator, but we can also perform slicing, so from to. And actually label-based slicing with text data on the index is not the most relevant case in practice, so there's hardly any reason why you should slice from Michael Phelps to Carl Lewis, but this is a good example to show you some pitfalls when slicing an index with duplicate entries. And in practice, label-based slicing is heavily used with datetime data in the index, a so-called datetime index, and you will see this in later sections of this course. But for the time being, let's assume that we want to get all rows from the very beginning until and including the row with Spiridon Chasapis. And actually, this is pretty straightforward with the log operator, so let's code summer.log. And then we can say that we want to have all rows from the very beginning until colon Spiridon Chasapis. So let's copy this and let's paste. And let's run the cell here. And here we have all rows starting with Alfred Hayos until Spiridon Chasapis. And it's important to see the difference between ilog and log. So with ilog, the left boundary is included and the right boundary excluded. And in contrast to that, here with the log, both boundaries are included, so the left and the right. So here we have all rows from the very beginning until Spiridon Chasapis, including. And now let's try the same with Michael Phelps. So let's copy and paste. And let's assume that you want to get all rows from the very beginning until Michael Phelps. So let's run here. And here we get an error, and it says that it cannot get the right slice bound for the non-unique label Michael Phelps. So Michael Phelps is a duplicate in our index, and therefore we cannot perform slicing operations with Michael Phelps. And the reason is pretty simple, so Panda simply does not know to which occurrence of Michael Phelps to slice. So should Panda slice until the first or the second or the third occurrence? So Panda simply does not know this. And actually we almost get the same error message if we try to slice from Michael Phelps to the very last row. So let's copy and paste here. And let's try to get all rows from Michael Phelps until the very last row. And also here we get an error message, and this is almost the same. But here it says that it cannot get the left slice bound for non-unique label Michael Phelps. So Panda simply does not know from which occurrence of Michael Phelps to start with. Alright, now let's have a look at the first 20 rows with the head method. So let's focus on the entries Dimitrios Drivas and Arthur Blake, and I can tell you that these values are unique, and therefore we should be able to slice from Dimitrios Drivas including until Arthur Blake including. So let's try this out. So let's copy here Dimitrios Drivas. So from him until Arthur Blake. And obviously this works. So we are starting with Dimitrios Rivas, and finally we are ending at Arthur Blake. And actually the same we can also do on the right hand side of the comma. So we can slice the columns from city till discipline. And by doing so, we get all columns from city including until discipline including. Finally, let's try the following. So let's first of all copy the code here. And let's assume that we want to get labels that actually do not exist in our data frame. So let's create here a list with Michael Phelps. But then we can also try to get Donald Duck. And this obviously does not work, and we get here an error message, and it says that passing lists to log with any missing labels is no longer supported. So this was supported until I think it was version 0.22 or 23, and then it was deprecated. And finally now with version 1.0 it's completely removed from Pandas. And actually the same applies also for missing column labels. So let's copy and paste here. And let's try to get rows with Michael Phelps. And column-wise we want to get 2 columns. So the columns here, and this actually does exist. And we assume that we also have the column H with the age of the athlete. And let's try to do so. And also here we get an error message, and it says that again passing list likes with any missing labels is no longer supported. However, we can use in these cases the reindex method. And that's exactly what we will do in the next lecture. So hope to see you there. Bye. This is the first lecture on Pandas series, and we've already learned that Pandas data frames, Pandas series, and Pandas indexes are the 3 major classes or data types in Pandas. And when selecting only one column or one row of a data frame, we typically get a Pandas series. So let's have a look, and we import Pandas and also the Titanic data set. And we already know that we have 9 columns in the Titanic data frame. And then we can select one column, for instance, the H column with the square brackets notation. And this gives a Pandas series. So let's also check this here with the type function. And actually a Pandas series is a one-dimensional labeled array. So we have an array with 891 elements. And these elements are labeled with the very same index labels that we have in the data frame, and it's here a range index. So the passenger with index label 0 is 22 years old, and we can find the very same passenger also here in the data frame. And we've already learned that there's also a second alternative how to select one single column, and it's with the data attributes notation Titanic.h, and this gives the very same result as the square brackets notation. So let's say for the H column in the variable H. And actually Pandas data frames and Pandas series share most of the methods and attributes. So there are only very few methods that are only available for data frames, and very few methods that are only available for Pandas series. And for instance, let's try to call the head method on the Pandas series H. And this works. So here we have the first 5 elements. And we can also customize this and select, for instance, the first 2 elements. Then next also we can call the tail method on the Pandas series H. And there's the attribute dtype. And here we can check the data types in the Pandas series. And it's no surprise that it is float. Then next we can check the shape. And here we get the result that we have 891 elements. And then we can also pass a Pandas series to a Python built-in function, for instance, the length function. And also here we get the number of elements in the Pandas series, 891. Now we've already seen that a Pandas series is a one-dimensional labeled array. And we can also get the labels or the index with the index attribute. So here we have the range index from 0 till 891. Then next, let's try to call the info method on our Pandas series H. And here we get an error, and it says that the series object has no attribute info. So the info method is only available for a Pandas data frame. And finally, there's the method toFrame, and with toFrame, we can convert a Pandas series into a Pandas data frame with only one column. So let's have a look here. And here we have now a data frame with the column H, and of course still we have on the left-hand side the range index. And now we could also call the info method on our data frame, so this is kind of a workaround. And this works pretty well. So here we can see that we have only one column, it's the H column. Alright, these were the very first steps with the Pandas series, and in the next lectures we will go into more detail, so hope to see you there. Bye. Alright, in this lecture we are going to perform a detailed analysis on numerical columns, or to say on Pandas series with numerical data, and we have still saved the H column, so the Pandas series H. And here we can see that we have numerical data, so we have the data type float, and with the describe method we can get some summary statistics on numerical columns. So for instance, we get the count, which is the number of non-null or non-missing values. It's 714, and we know that we have 177 missing values. Then we get the mean or the average age, which is 29, then the standard deviation. And then we can see that the youngest passenger is 0.42 years and the oldest 80 years old. Then we have the median, which says that 50% of all passengers are younger than 28. And also we have the 25th and the 75th percentile. And actually 25% of all passengers are older than 38. Now, for most of the summary statistics in the describe method, there's also a special method, and for instance we have the count method, and of course also here we get 714, and let's go here inside, and it says that it returns the number of non-missing values or observations in the series H, and this shouldn't be mixed up with the size attribute. So here we get the number of all elements including missing values, 891. And we have already seen that if we pass H to the built-in function length, then we get the total number of elements, 891, but not the number of non-missing values. So now let's come to a very important aspect, and the real power of the Pandas library is that Pandas is specifically designed to handle real-world data. And real-world data is typically messy and unclean. For instance, many real-world datasets contain missing values, and Pandas is really powerful when it comes to handle missing values. And one example is the sum method. So here we can get the sum over all elements in the H column, and it's 21,000. And now we can try to do the same with the Python built-in function sum. And here we get nan. And the reason for this is that the sum function simply does not know how to handle the missing values. And in contrast to that, the sum method by default can handle missing values. So let's go here inside. And here we have the very important parameter skip NA. And actually the default setting is true. And here it excludes the missing values when computing the result, so the sum. So we have here skip NA, and the default setting is true. So by default, Pandas simply ignores the missing values when calculating the sum, and this works. But of course, we can also set skip NA to false. And also here we get missing values, because if we include the missing values, then Pandas does not know how to calculate the sum. And actually we can find the skip an A parameter in many Pandas methods, and typically it's set to true. So by default Pandas just ignores missing values. And another example is the mean method. So here we can calculate the mean or the average age, which is 29. And let's go here inside. And also here we can see that we have the skip an A parameter. Next, we can also calculate the median or the 50th percentile. And also here we have the skip an A parameter. Then we can also calculate the standard deviation and the minimum value and the maximum value. Now we are coming to the very helpful method unique, and let's go here inside. And it says that unique returns the unique values in our series. So it actually removes duplicates, and the unique values are returned in order of appearance. So let's run the cell here. And here we get 22, 38, and so on. And also here we can see that the missing value is also included, NaN. And let's also check the number of unique elements. So with the length function, we get 89. And there's actually a special method to get the number of unique values. It's the NUnique method. And here we get 88. So we have here a difference of 1. And the reason is pretty simple. So let's go here inside the NUnique method. And it actually returns the number of unique elements in our Pandas series. And by default, it excludes the missing values. So we have here the parameter drop an A, and the default setting is true, but we can also set this to false. So this is the default setting, and it returns 88. But here above, we can see that the unique method by default also returns a missing value. And if we count here the number of elements, it's 89, including missing value. But we can also get the number of unique values, including missing values, with NUnique by passing false to the drop an A method. And by doing so, we include missing values. So let's run, and now we get 89. The value counts method is a very useful and versatile method. And the default behavior is that it returns the number of occurrences, or to say the absolute frequencies of all unique values, sorted from most frequent to least frequent. So let's run the cell here. And the most frequent age is 24, and we have in total 30 passengers who are 24 years old. Then next we have 27 passengers at an age of 22. And finally we have values with only one appearance, so for instance 0.42 or 23.5. And actually value counts gives us some options to customize our analysis, so let's go here inside. And here we can see that we have 5 parameters: normalize, sort, ascending, bins, and drop an A. And we will have a look at all of these parameters. And first of all, let's focus on the sort parameter. And again, the default argument is true. And here the unique values are sorted from high frequency to low frequency, but we can also pass false to sort. And in this case, the unique values are returned in order of appearance. So the very first passenger is 22, then the second passenger 38, and we can also check this here. So 22 and 38. Then next we can decide whether we want to have NA or missing values in our analysis. And there's the parameter drop NA. And the default value is true, so by default we ignore missing values. So here we do not see any missing values, but if we pass false, then missing values are included in our analysis, and obviously the most frequent value is NaN missing value, so we have 177 missing values. We have already seen that the unique values are sorted from most frequent to least frequent. And the reason is that the default argument for the ascending parameter is false. So by default, we have a descending order. So from high to low, from most frequent to least frequent. So that's the default behavior, but we can also set the ascending parameter to true. And by doing so, we sort the unique values from least frequent to most frequent, or to say from low to high. And here we are starting with the value 0.42 with the frequency 1, and finally we end at the age of 24 with 30 occurrences. And actually by default, Pandas returns the absolute frequencies, but we have also the option to return the relative frequencies. So first of all, let's explicitly pass the default arguments to sort, drop NA, and ascending. And then we have the additional parameter normalize, and the default argument is false. So by default, we get the absolute frequencies, but we can also change this, and we can pass true to normalize. So let's run the cell here, and by doing so, we get the relative frequencies. So to say 4.5% of all passengers are 24 years old, and 3.7% of all passengers are 22 years old, and so on. Now the question is, how does Pandas calculate the relative frequencies? And let's focus here on 24. So we have the absolute frequency of 30, and the relative frequency is 4.2%. And this is simply 30 divided by the number of non-missing values, 4.2%. It's important to understand that here in the denominator we have the number of non-missing values 714, since we ignore the missing values as drop NA is set to true. But if we set drop NA to false, then in the denominator also the missing values are included, and therefore the relative frequency changes from 4.2% to 3.3%, and also here we have then the relative frequency of missing values. And actually what happened under the hood is that in the denominator we have now the total number of elements in the age column. So we have here size, and here we get 3.3%. And finally, we have the bins parameter. So again, we have the default arguments for all of the other parameters. And let's have a look inside here. So we have bins. And here we can group the unique values into half open equal width bins. So for instance, we could pass 5 to bins, and then we get 5 bins with equal range or equal width. So we are starting here with the interval from 0.3 to 16, and the width is here 16 years. Then we have the second bin from 16.3 to 32.2, and so on. And here on the right hand side we can see the number of occurrences in the intervals. So 346 passengers are between 16 and 32 years, and the least frequent interval is here between 64 and 80, so only 11 passengers are in this interval here. And of course we can also change the number of bins, so for instance from 5 to 10. And in this case the first interval is from 0.3 to 8.3, and the last bin from 72 till 80. And also here the default behavior is that we get absolute frequencies, but when we pass true to the normalize parameter, then we get the relative frequencies. Alright, there's one last thing that I want to highlight, and probably you've already noticed that the output of value counts is a Pandas series as well. So this is here a Pandas series, and also this. And as the values of the Pandas series, we have the absolute or relative frequencies. So here we have absolute frequencies and here relative frequencies. And on the left-hand side, as the index of our Pandas series, We have the unique passenger ages, or also the bin saw and turbines. And this makes it pretty easy and comfortable to continue with any further analysis, as we can simply use method chaining. So for instance, here we have the relative frequencies, and I would suspect that the sum of all relative frequencies is 1, and we can check this by simply chaining the method sum. And now let's run again, and here we get 1. Alright, we have reached the end of this lecture, and I hope to see you also in the next video. Bye. Hi everybody. In this video we analyze the Pandas series with non-numerical values, so for example string objects like names. And therefore we work with the Summer Olympics dataset, and first of all we import Pandas. And we import our Summer Olympic medal dataset, and we will have a look at the first 5 rows. So you can see here each row is actually a medal that was awarded during Summer Olympic Games. And here in the columns we have the year of the Olympic Games, the host city, the sport, the discipline, the athlete who won the medal. So here in this example Alfred Hayos won the gold medal. And he's from Hungary, and he's a man. And the event was 100-meter freestyle. And let's check also with the info method. We have in total 31,165 medals that were awarded from 1896 to 2012. We have 9 columns. And we have more or less no missing values. So only here in the country column 4 missing values. And our year column contains integers, and all of the other columns contain actually string objects. And now starting from our data frame here, we can create a Pandas series with non-numerical values. So for example, we slice for the column athlete, and we assign the column athlete to the variable athlete. So let's do this. And first of all, we can check the type of our column here, and it's a Pandas series. And let's have a look at the first 5 elements or rows of our Pandas series. So here we have the values. These are the athletes on the right side, and on the left side we still have the index of our Pandas data frame. And we can also have a look at the last 5 rows. And we can also check the data type of the values within our Pandas series. So it should be here, string. We have here O for object. So in simple words, when we have an O here, it's very likely to have string objects actually. And we can also check the shape of our Pandas series, and we have a one-dimensional array. So a Pandas series is always one-dimensional. And we can also try to use the describe method. And the describe method gives us actually different results compared to a numerical series. So here for non-numerical series we get first of all the total count of elements. So we have 31,165 athletes, and 22,762 are actually unique. So we have many athletes that won more than one medal. So for example Michael Phelps, who is actually the top athlete who won the most medals, and it's here frequency. You can see Michael Phelps won 22 medals. And we can also check here the size of our Pandas series. It's 31,165. And with the count method, you can also check for the amount of non-null values, and this is here the same as with the size attribute. So in our athlete column or Pandas series, we do not have any missing or NaN values. So if we had NaN values, then the count method here would return a lower value than our size attribute. And the difference would then be actually the amount of missing values. And we can also try to apply the min method. So for a numerical series, we get here the minimum element, and with non-numerical values, we get here alphabetically the very first athlete, and it's Edgar, I don't know how to pronounce it here, but it starts with a double AB. So alphabetically this athlete is actually the very first athlete. And we can also check our Pandas series for unique values. So here are all unique values, or to say athletes that won a medal in some Olympic Games. And we can also count the number of unique athletes. With the length function, it's 22,762. And we can do the same with the method nUnique. So it also returns us here 22,762. And with nUnique we can decide whether we want to skip missing or NA values or not. And as we do not have any missing values here in our athlete series, so the result should be the same actually. So default value is true. And if we change to false, so we should also get the 22,762 because we do not have missing values. Alright. And last but not least, we can also use here for the non-numerical series the very powerful method value counts. And what value counts actually does, it returns us a Pandas series with actually the frequency of all values that appear in our Pandas series. So here we can see Michael Phelps is 22 times in our athlete Pandas series. That means that Michael Phelps won 22 Olympic medals in his career. And value counts by default returns us here the frequency in sorted order. So actually in descending order. So the value with the highest frequency comes first here, and it's Michael Phelps. And the second most successful athlete is here Larissa Latinina, and so on here. And we can scroll down, and in the end we end up with athletes that won one medal here. And with the ascending parameter we can also change the order of sorting. So here now we are starting with the athletes that won one medal. And in the end we have here also Michael Phelps. And we can also normalize our results with the normalize parameter. So the normalized parameter does not return absolute frequencies, but relative frequencies. So we have 31,000 about medals, and Michael Phelps won only 0.0706% of all medals. Alright, now we are finished with this session. In the next sessions we will see and learn how to create Pandas series. So hope to see you there. Bye. In this video we learn how to sort Pandas series. So let's assume we have the age column of our Titanic dataset, and we want to sort the age from young to old or from old to young. And we can do this with the sort values method. So that's option number one. We can sort a Pandas series by values, but we can also sort a Pandas series by the index. So let's go into our examples here and we import Pandas. And then we create a dictionary with daily sales. So we have on Monday, so 1 stands for Monday, we have 10 sales. Then we have Wednesday, 25 sales. And then we have Tuesday, 6 sales. So our dictionary here is not really sorted. So Wednesday comes before Tuesday. Then we have Thursday, 36 sales. Then Friday, 2 sales. Saturday, 0 sales, because we do not work on Saturday. And Sunday, as we do not work on Sundays as well, we have also 0 sales, but instead of having here 0, we have just here none. So we can do this, and let's see what we get here. We get here a dictionary with weekdays values pairs, and you can see here on Sunday it's still the value none included. So let's pass our dictionary to pd.series, and let's create a Pandas series. So now you can see here our Pandas series with on the left side our keys of our dictionary, and in the same order as we passed it. So beginning with day 1, and then day 3, day 2, 4, 5, 6, 7. So here again. And we also have on the right side the values. And here you can see on Sunday we have a NaN or missing value. So the keyword none actually transforms in a Pandas series in a Pandas data frame to a missing value NaN. And as we do not have here the right sequence in our index, so starting from Monday but then having Wednesday and then Tuesday, we can sort our index with the sort index method. So now you can see we have our index sorted starting from 1, and then we have 2, 3, 4, 5, 6 and 7. And we can also determine whether we want an ascending or descending order. So by default here we have an ascending order starting with the lowest index, so here 1. So here with the sort index method we have a parameter ascending, so let's press Shift Tab here and have a look. So here we have the ascending parameter, and by default it is set to true. So let's run again here. So we have here the ascending order, but we can change this to the descending order by setting the parameter to false. So now we have the descending order starting from Sunday, or from 7 here, 7, 6, 5, 4, 3, 2, 1. Alright, so now let's change it back to ascending order. Alright, so now we have changed here our Pandas series sales by sorting the index, and let's print again our Pandas series. And now you can see here that our change, so sorting the index, is not stored in memory, so we haven't actually changed our series here. And what we did here actually, we just created a copy of our Pandas series sales, and we sorted the index of the copy only. But yeah, what if we want to change our original series, and there's a solution for it. So let's go inside the sort index method and check with Shift Tab, and here is the parameter in place. And in place is by default set to false, and if it's true it performs the operation in place. So what in place is doing, if it's set to false, all changes we made, so for example sorting the index, are performed only on a copy, and the original series has not changed. And if we set the in-place parameter to true, then all changes also apply for the original series, so the change is in place. And the in-place parameter in Pandas is a very important parameter, and you can see it in many methods for Pandas series and also for Panda data frames. And it helps you a lot to understand if a change is actually made on a copy or on the original Pandas series or data frame. And yeah, depending on what you actually want to do, you can set the in-place to true or false. So let's explicitly here introduce the in-place parameter, and by default it's set to false. So now here we created a copy of sales and sorted the index, and if we print our original sales, it's still not in place, the change here, but if we change the in-place parameter to true, and now you can see here we do not see any printed copy of the sales, so that's the first good indication that we changed the original sales Panda series. And let's print here our Panda series. And now we can see that, yeah, the change is in place. So here we sorted our index and we changed our original Panda series sales. Alright, so now let's head over to sorting values. So far we only sorted our Panda series by the index, and we can also sort our series by the values. And we set in place to false. And let's see what we get here. So by default, the in-place parameter is set to false, so I only want to make this explicitly here. And we can see here on the right side, we have sorted our sales Panda series by the values and in an ascending order. So starting from 0 sales on Saturday and ending with 36 sales on Thursday. And the NaN value is at the very end. And also for the sort values method, there are some parameters. So we have the ascending parameter where we can determine whether we want to sort in an ascending or descending manner. So by default, the ascending parameter is set to true, but we can set it to false. And let's check here. So now we sorted our values in a descending order, starting with the highest value, 36, on Thursday. And we can also determine here, you can see that still our NaN value is in the last position, and we can also determine the position of Na values. So here we have last, but we can also change this, for example, to first. So now here we have our NaN value at the first position. But in the end, so it makes more sense to have it at the last position. And sorting our sales from high to low makes sense. So we keep ascending equals false. And once we are happy here, we can set our in-place parameter to true. And in this way, we save our changes actually in our original Pandas series. So let's run here and let's print our series. And here we can see that the changes we make here are in place. Alright, so now let's again create our dictionary, and now with Monday, Tuesday, Wednesday and so on as strings. And we can pass also this dictionary to pd.series and create a Panda series. Let's have a look here. And now if we sort the index with the sort index method, then let's see what we get here. So then our index is actually sorted in an alphabetical manner. So Friday starts with an F, and then we have Monday with M, Thursday, Tuesday and Wednesday. So if we have a numerical index, then the numerical index is sorted from high to low, and with a string index it's sorted alphabetically, and we can also change here the order from ascending to descending. So now it's starting with the Wednesday. W. Alright, so now we are finished with this video. In the next video we'll have a look at the methods n largest and n smallest. So hope to see you there. Bye. In this video we learn how to filter our data frames, and so far we selected rows of a data frame only by index position or index labels. So for example, we selected the first 20 rows, or we selected all rows with the index label Michael Phelps in our Summer Olympics data set. And actually in real world, the more important case is to filter a data frame based on information in one or more columns. So for example, in our Titanic data set, we want to filter all male passengers on the Titanic, or we want to filter all passengers that are younger than 14 years old. And first of all, before we start, let's import Pandas. And we are working with the Titanic dataset, and we will have a look at the first 10 rows here. And what we want to do now is we want to filter out all rows where the passengers are male. So in the end, we want to create a data frame with only passengers that are male, and therefore we select our sex column, and we will have a look here at the first 10 elements in our sex column. So here you can see our sex column. And now we want to check element-wise each element if the element is male or female. And this works essentially the same way as with NumPy arrays. So let's use here the double equal sign, and let's see what we get here. We get actually here a brand new Panda series with Boolean values. And Pandas does this in a vectorized manner, so we do not need any for loops like with lists. So Pandas checks here for each element. So let's start here with element 0. Here we have a male, and male is equal to male, so we get a true here. Then we have 3 times female, and then we get here 3 times a false, and then again 4 truths. So now here we have a Panda series with Boolean values for each passenger, if it's a male or female. So from index position 0 to 890 here. And now we can filter our data frame, and we can pass here our Panda series with Boolean values into spare brackets of our Titanic dataset. And this works essentially the same as with NumPy arrays. So by passing our Boolean series here within the spare brackets, we filter out all rows where the passenger is male. So let's try here. And we get here a brand new data frame with only male passengers. And what Pandas does here, Pandas checks the row-wise if we have a true or false in a row. So for example, let's go back here to our Panda series, and we can see here, so in row 0 we have a true, and in our new male data frame we have also the row with the index position 0, and in index position 1, 2 and 3 we have a false. So in our new data frame we do not have the rows with the index position 1, 2 and 3. And then again for the index positions 4, 5, 6, 7 we have a true, we have a male, and in our new data frame we have here the rows 4, 5, 6, 7. Alright. So let's copy here our code. And what we can also do, instead of having here the square brackets notation, we can also use the log notation and filter for all rows where the sex column is male. So this works as well. So we have here the same result, actually, the same new data frame. And if you ask me which notation to use, I would clearly recommend the log notation, and that for two reasons. So first of all, with the log notation, we can also filter here not only for rows. So here we want to have all rows where we have a male. And in addition, we can also filter for columns. So we can make here a comma, and then we can say, okay, I want to have only the fair column. So for all male passengers, I want to know the fare they paid. And now here we have a Panda series with all the fares that the male passengers paid. And with the spare brackets notation, you cannot do this within here one spare bracket. So let's go back. So here in this case, if you want to filter or only select the fare column, you have to add here another spare bracket and filter for the fare column. So this gives actually here obviously the same result. So the first advantage of the log notation is actually that you only have here one spare bracket, and the code is actually easier to read, and it's more comfortable. And here you have two spare brackets, and this is a so-called chained indexing. So what you are doing here, you actually chain index operations. So first of all, you filter the data frame for only males, and then in a second step, you select only the fare column. And chained indexing is actually a very bad way to filter your data frame, because it creates huge problems and confusion when it comes to manipulating data frames, so changing elements in the data frame. And we will see and check this later in our course, so chained indexing is not a good idea. And if you are already familiar with Pandas, you might have learned filtering here with the spare brackets notation. But this is a clear recommendation from my side. Please use here the log notation. So again, as I said, when it comes to manipulating data frames, you will have less problems with the log notation than here with the spare brackets notation. Alright, so now let's move on here. And as a matter of taste, we could also call our Pandas series with the Boolean values here, Titanic.sex equals male. We can also assign the variable mask. So here mask 1. And again, here we get our Boolean series. And to increase the readability of our code, we can now also pass mask 1 to our log operator here and filter our Titanic data set in this manner. So this gives us, of course, the same result, but it's a bit clearer and it improves the readability. So this is a better style than passing here the whole line here into the spare brackets. But the result is the same, of course. And what we also did here, actually, we saved our brand new data frame with only the male rows to the variable Titanic male, and we can now print and check our new data frame. We check the first 5 rows, and we have here our brand new Titanic male data frame with only male passengers. And with the log notation, we not only can filter for specific rows, but we can also filter specific columns. So we learned that before, but we can do more than just filtering, for example, the fair column or the age column. What we can do actually, we can check here the data types of our columns with the attribute titanic.dtypes. And here we got the data types of our columns. So in the survived and passenger class column, we have integers. In the age and fair column, we have float objects. And also here in the zip_sp and parch, we have integer objects. And in the sex, embarked and deck column, we have actually strings. And now what if we want to filter our data frame? So we want to have all rows where we have a male, and we only want to have the columns with numeric objects. So we want to filter for the columns survived, passenger class, zip_sp, parch, and fair. And we do not want to have the string columns sex, embarked, and deck. So now we could check for each column if the dtype is object and call it mask2. So now we have here for the sex column, the embarked column, and the decked column are true, because here we have string objects. And then we can also filter our Titanic data frame with the log notation. So we want to have all rows, and we want to have the opposite of mask2 with the tilde symbol here. So if we would filter for mask2, we would get all columns with string objects, and with the tilde symbol, we get all columns with actually numeric values here. So let's try this one. So here we get all rows of our Titanic data frame with only numeric columns here. And we can further customize here our filtering and pass mask1 and the opposite of mask2. And then we get here all rows where we have a male passenger, and we only get the columns that have numeric data. So we have survived, passenger class, age, zip_sp, parch, and fair. So here with the log notation, we can not only filter for rows, but also for columns. And with the spare brackets notation, this wouldn't be as easy as we have it here with the log notation. Alright, so now we are finished. So the key message is, when we want to filter data frames based on a condition that is in a column, we should always use the log notation. So that's here a clear recommendation from my side. Alright, so see you in the next session. Bye. In this video we learn how to filter data frames based on many conditions that must all be met. So first of all, we import pandas, and we are working with our Titanic data frame. And here we have the first 10 rows. And from the movie we know that after hitting the iceberg there was a clear code of conduct to first save all women and children. So women and children had priority for the few lifeboats that were on board. And therefore we can make the hypothesis that being an adult man was a pretty bad combination for surviving the disaster. And yeah, actually what we want to do, we want to check now if the data supports our hypothesis. So we want to filter all male that were older than 14 years old. So we use here 14 years, but we could also use 16 or 18 years. And actually we have two conditions. So the passenger must be a male, so titanic.sex equals male. And we store here the Boolean series in the mask1 variable. And the second condition is that the age must be greater than 14. And we save the resulting Boolean series in the variable mask2. So let's check here, and we check the first 5 elements of each mask. So now we have to combine both conditions with an AND operator, and only if both conditions are met we get a true. So for being an adult male, the person must be a male and it must be older than 14 years old. So we can here use the AND sign and combine mask1 and mask2 with the AND sign, and we will have a look at the first 5 elements. So let's go to index position 0. Here we have true, and true gives true. Then index position 1 we have false, and true gives a false because both conditions must be met. And at index position 2 we have false and true again, and we get a false, and so on. And now we can pass mask 1 and mask 2 into our log operator, and by doing so we can filter out all rows where we have a male passenger that is older than 14 years old. And we can also select here for the columns. So we are only interested in the survived column, in the passenger class column, in the sex column, and in the age column. So we create here a brand new data frame, and we store the data frame in the variable male survived. So let's run here the cell and check the first 5 rows of our new data frame. And here we have our new data frame where we have only male that are older than 14 years old. So we can also check, let's say, 20 rows. So only male passengers and only male that are older than 14 years old. So this works here. Alright, so now we can also get more information on our new data frame with the info method. So we have in total 414 passengers that are male and older than 14 years old. And let's use the describe method. So we have 414 passengers. And we actually know that in the survived column we have a 1 for survived and a 0 for not survived. And we have a mean here of 0.17 in our survived column. This means that only 17% of all male passengers that were older than 14 years old actually survived the Titanic disaster. And let's recall the survival rate for all passengers. So let's use the describe method on the total data set here. And here we can see that on total 38.3% of all passengers survived. But in the subset of male passengers older than 14 years old, only 17% survived. So it's pretty likely that our hypothesis is true, that being an adult male passenger on board of the Titanic was a pretty bad combination for surviving the disaster. Alright, so now we are finished with this session, and hope to see you in the next session. Bye! In the last video we learned that being an adult male on the Titanic was a pretty bad combination for surviving the disaster. So now we want to check the opposite hypothesis, and we know that there was a clear code of conduct to save women and children first. And what we want to do now is actually we want to check if being either a female or a child was favorable when it comes to surviving the disaster. So first of all we import pandas, and we work with our Titanic data frame. And we have actually 2 conditions. So we want to check if we have a female, and we store the resulting panda series with Boolean values in mask 1. And as a second condition we check whether the age of the passenger is less than 14, and we store this in mask 2. So now we have here 2 panda series with Boolean values. And now we want to combine both conditions with an OR operator. So we have to use here the pipe symbol as OR. And the pipe symbol stands for the logical OR. So by combining mask 1 and mask 2 with the pipe symbol, we should get all passengers that at least meet one condition. So we should get adult females, we should get young boys. And at least one condition means that we also should get all passengers that meet both conditions. So we also should get girls below 14 years old. So let's combine here mask 1 and mask 2, and let's have a look here. So we get also here a Boolean series. So if we have a look at index position 0, we have false or false. So no condition is met and we get a false. And let's have a look at index position 1, where we have true or false, so at least one condition is met and we get a true. So here we have no example where we have 2 times true, so maybe let's increase here to 10 rows. That's still not enough here, maybe 20 rows. So I'm searching now a young girl. So here at index position 10, we have a true for the female, so it's female, and also we have a true for being younger than 14. So we have true or true, and this gives us, by combining it with or, this gives here also a true. And now we can pass the combined Boolean series here to our Titanic dataset and the log operator. And by doing so, we are filtering out all rows that meet at least one condition. So let's check it here. So here we have adult females, then we have a baby male, adult females, a very young female here, a very young male here. So we created here a brand new data frame with only females and young boys. Alright, so now we can further filter our data frame. So we again use mask 1 or mask 2, and we are only interested in the survived column, in the passenger class, sex and age. So we are creating here a brand new data frame, and we are storing the data frame here in the variable women or children. And let's check here our new data frame, the first 5 rows. And let's get more information on our data frame here. So we have 351 entries. So we have 351 passengers that are either women or children. And let's use the describe method to get even more information. And we see here in the survived column, so we have a mean of 0.72, and that means with being either a woman or a child, the probability of surviving the disaster was actually 72%, and that's quite high actually. So we can also compare this to the survival rate of all passengers, and we already know that the survival rate of all passengers was only 38%. So actually our dataset supports our hypothesis that being either a woman or a child was a very favorable characteristic on board of the Titanic to survive the disaster. Alright, so now we are finished with this session, and I hope to see you in the next one. Bye! In this video, we create a new column for our data frame, and the values of our new column are based on values of other columns in our data frame. So this video is meant to be a gentle introduction to the topic, and later in part 2 we will dive deeper into it. So first of all, let's import Pandas, and we import our Titanic dataset, and we will have a look at the first 5 rows. And now let's assume that we want to know the year of birth for all passengers, and we know that the Titanic disaster was in the year 1912, and in the age column we already have the age of the passenger in that particular year 1912. And what we can do now, we can calculate the approximate year of birth by subtracting the age of each passenger from 1912. So for example, a 12-year-old passenger was likely born in 1900, so 1912 minus 12. So the actual year of birth should be between 1899 and 1901, so plus minus 1. And the good thing about Pandas is that the same as NumPy arrays, we can perform element-wise or vectorized operations. So we can do this for whole data frames and also for Panda series. And that means that we do not have to use for loops here. So we can just make a vectorized operation by subtracting the age series from 1912. And let's see what we get here. So here we can see for the first passenger we subtracted 1912 minus 22 gives us 1890. And for the second passenger, we subtracted 1912 minus 38, gives us 1874. And Pandas does this in a vectorized manner, element-wise, for each element in our Titanic H series. Alright, so now we can create a new column called the year of birth, and we can calculate for each row 1912 minus the row-specific age. So let's see what we get here. And let's have a look here at our new data frame. So we created here a new column, year of birth. And for each row here, we see the result of the subtraction 1912 minus the respective age here. Alright, so now let's move on, and we have here a column SIP-SP, so this stands for the amount of siblings and spouses for each passenger on board. And we have the column PARCH, and this stands for the amount of parents and children for each passenger on board. And what we can do now, we can add those two columns, and then we get the total number of relatives for each passenger. So for example, passenger number 1 had maybe his spouse on board and no parents and no children, and the total amount of relatives on board is actually 1, so 1 plus 0. So we can add those two columns in a vectorized manner. So for each row we have an addition of the two values. So we have the first row 1 plus 0 gives 1. Then the second row 1 plus 0 gives 1, and so on. And now we can create a new column called relatives, where we add the values of the SIP-SP column and the PARCH column. And let's have a look here. So here on the right we created our new column with the amount of total relatives for each passenger. And what we can do now, actually, we can now drop the columns SIP-SP and PARCH, because we are happy only with the relatives column. So we are not interested if there are siblings or spouses or parents or children. So the only thing we are interested is how many relatives are on board of each passenger, and therefore we can drop the two columns with the drop method. And we pass in a list the columns SIP-SP and PARCH to the columns parameter and set the in-place parameter to true. And let's check again here. And now here we have removed the SIP-SP and PARCH column, and we only have the relatives column here. Alright, so and also we have here the fare column, and the fare column gives us information about the price that each passenger paid for the trip. And for example, the first passenger paid for the trip $7.25 or pound. So I'm not sure if it's dollar or pound here. However, these are prices that the passengers paid in 1912 with 1912 prices, and we can make inflation adjustments until today to get a feeling how expensive a ticket was in today's prices. And therefore we can introduce an inflation factor. So I randomly choose here the inflation factor 10. So I didn't check the cumulative inflation in the last 100 years. So and the factor means that $1 in 1912 is actually worth $10 today. And now we can multiply the column fare with our inflation factor, and we get the inflation adjusted price today. So the first passenger paid actually $72.5 or pounds in today's prices, and the second passenger paid $712 or pounds, and so on. And what we can do now, we can either introduce a new column and call it, let's say, fare today prices, or we can just override the existing fare column with the prices of 1912 and assign the new values with the multiple 10. So we now here we override the fare column by passing the values times 10. So let's see what we get here. So we didn't actually create a new column, but we override our existing column, and here we have the ticket prices in today prices, so 72.5 and 712. Alright, so now we are finished with this video, and I hope to see you in the next video. Bye! In this video we learn how to apply user-defined functions to rows to columns, or even to all elements of a data frame. And we can do this with the methods apply, map, and apply map. So first of all, let's import pandas. And in this video, we are working with the sales dataset, and therefore we are importing the dataset from the CSV file sales.csv. And let's have a look here at our sales dataset. And here we have on the left-hand side 4 salesmen, Stephen, Mike, Andy, and Paul. And here in our data frame, we have actually the sales data, so for Monday, Tuesday, Wednesday, Thursday, and Friday. And here for Stephen on Thursday, we have also a missing or NaN value. So no problem here, this happens in reality. And let's have also a look here with the info method. So we have integer data types, and we have obviously here one missing value in the Thursday column. And now let's assume that we want to calculate for each weekday the minimum sales. So for example, for Monday, the minimum sale for all salesmen is here 17, Andy. And for example, for Tuesday, the minimum sales is here Mike with 9, and so on. And actually we can do a lot of things in pandas with built-in methods. And there's also the built-in method .min. And the min method we can apply on a data frame. So here our sales data frame. And then we can define here the axis. So we have the choice between index and columns. And if you want to calculate the column-wise minimum, so for each column the minimum, we have to pass 0 here. And 0 stands for index because we are calculating the minimum along the rows or along the index. And in my opinion, this is not really intuitive. So if I want to calculate the minimum for all columns, so column-wise, it would actually be more intuitive to have here axis equals to 1, which stands for columns. But actually we have to pass here axis equals to 0, which stands for calculating the minimum along the rows or along the index. So again, this is not really intuitive, but it is as it is actually. And let's calculate the minimum for each column. So let's do this here. And here we can see we have the minimum for each column. So here we have for Monday 17, for Tuesday 9, for Wednesday 15, and so on. And we can also determine the minimum for each row, so for each salesman. So for example, the worst weekday for Stephen was 15. If we exclude here the missing value, then the worst day for Mike was Tuesday with 9 here, and so on. And instead of passing here 0 to the axis parameter, here we have to pass 1 to the axis parameter, which stands for columns. So here we want to determine the minimum along the columns, or actually row-wise, so for each row. So let's do this here. And here we get the minimum for each salesman, so for Stephen 15, for Mike 9, and so on. However, in reality, there are some tasks and operations that we want to perform, for which we do not have any built-in method, and therefore we have to create a built-in method or function. And we can do this here, for example, with the def keyword. And let's assume that we want to calculate, first of all, for each row, so for each salesman, but also for each weekday, the range between the minimum and the maximum value. So for example, for Monday, the maximum value is 87 and the minimum value is 17. So the range on Monday between maximum and minimum was 70. And we can actually do the same for each salesman. So for example, the maximum sales for Andy was 54 and the minimum 8. And therefore the range here is 46. And there's obviously no built-in method to calculate the range, and therefore we have to create a built-in function or method. So now actually we want to calculate for each column or for each row, and a column or a row is a Pandas series, so we want to define the user-defined function range, and we pass here Pandas series, so either rows or columns. And actually our function should return the maximum in our row or column minus the minimum. And this is here then actually the range of our series. So now let's define the function here. And then we have to apply the function to either all rows of our data frame or all columns. And we can do this with the apply method. So first of all, let's use here our sales data frame. And then we use the apply method. And let's check here inside the brackets. So the apply method apply a function along an axis of the data frame. So we can either apply the function for all rows or for all columns. And therefore we have also here the parameter axis, and by default it's set to 0. And also here axis equals 0 means that we apply the function for all columns or along the index. And first of all, this is exactly what we want here. So we want to calculate the range for each weekday. So let's set here axis equals to 0. And actually we have to define a function, and the function here should be our defined range function. So now let's run here the code. And here we can see that we get the range for all weekdays. So for Monday it's 70, so 87 minus 17. And for Tuesday we have here 58, so 67 minus 9, and so on. And actually we could also apply the range function on all rows by passing here 1 to the axis parameter. So here we have now the range for each salesman. For example, here for Andy we have 46. So here we have Andy, and we have the maximum of 54 minus 8 is 46. And instead of passing here a user-defined function that we created with the def keyword, we could also pass here a lambda function or anonymous function. So let's do this here. So we have here the keyword lambda. And this simply means that now we want to define a function, and we want to define the function for each series, for example. And then here after this we make a colon. And then we have to define the function that we want to apply on each series. And here in our case, it's here the maximum minus the minimum. So let's try this out here. And here we get actually the same result. And instead of defining here the variable series, we can also call here our variable or all elements where we want to apply the lambda function x. So this is a bit shorter, and actually it doesn't matter which name you take here or which variable name. And here we are. And the same we can actually do for all columns. So here we calculated the range for each row, and also we can calculate the range for each column. Alright. So now let's have another example, and therefore we import our Summer Olympic data frame. So let's have a look here. And instead of applying the user-defined function on all rows or all columns, we can also select a row or a column of our data frame and apply a user-defined function on each element of the row or the column. So for example, here we have our summer data frame, and we can actually select here the athlete column. So let's try this out. So here we have one column, and this is the Pandas series, not a Pandas data frame. And also here on a Pandas series, we can apply a user-defined function on each element of the series. So for example, here on Alfred Hayos, Otto Herschmann, Dimitrios Drivas, and so on. And again, we can do this with the apply method. And if we have a Pandas series here, we do not need here the parameter axis, because with a Pandas series, we have only one dimension where we have several elements here. So let's also press here Shift Tab. And if we have here a Pandas series, the apply method invokes a function on values of a series. And in this example, we want to extract for each element in our Pandas series here the very first character. So for example, we want to have for Alfred Hayos the H, for Otto Herschmann the H, for Dimitrios Drivas the D, and so on. And therefore we can define here a anonymous function, and X stands here for each element in our Pandas series, or for each name. And for each name we want to select the very first character. So let's try this out here. And here we get H, H, D, M, C, and so on. And here for Panda series, we can also apply a function on all elements of the Panda series with the map method. So let's copy here. And let's paste here. And instead of using the apply method, here we can also use the map method. So let's check here. Map values of series using input correspondence. So a dictionary series or a function. So on each element of our athlete column, we apply here the lambda function. And here we should get actually the same result as with the apply method. And this is true. Alright, so far we used here the apply method to apply a user-defined function on all rows of our data frame or on all columns of our data frame. And we've also learned that we can use the apply method to apply a user-defined function on all elements of a column. And for this task we can also use the map method. And now last but not least, we can also apply a user-defined function on all elements of a data frame. And we can do this with the apply map method. So we have here our summer data frame, and let's assume that we only want to work with the second and third column. So let's do this here. So here we have only the column city and sport. So these are both columns where we have string objects here. And now let's assume that we want to do the same as here above. We want to select the very first character of each element. So for example, here in the city column, here in the first elements, it's the A, and also here in the sport column. So again, here we have to use our lambda function on each string here. And we can do this actually with the apply map method. So let's try this out. And here we get for each element in our data frame the very first character. And actually we can do the same also for our sales data frame. So here we have our sales data frame. And these are actually the gross sales before deduction of any costs. And let's assume that the gross profit margin is 40% of the sales. And then in addition, all salesmen have actually a daily fixed cost of 5. So now we want to calculate the net profit for each salesman and for each day. So we have to apply here a function on each element, and we can actually create here a lambda function. So we calculate 40% of each element here. So this is actually the profit margin, and then we deduct 5 on each element. So this is the daily fixed cost. And we can actually apply the function here on each element, again here with the apply map method. And here we have the net profits for each daily sales. And of course in this example we could achieve the same result with some arithmetics. So we can simply say here we have our sales data frame, and we multiply each element by 0.4, and then we deduct 5. So this gives here in this example the same result. But as we have seen here, we can also apply here a user-defined function on all elements with the apply map method. So with this we are finished now with this video, and I hope to see you also in the next video. Bye! In this video we are going to plot the data on our Titanic data frame with the method plot. But first of all, let's import Pandas, and we import our Titanic data set. So here are the first 5 rows and some meter information. And if you want to create some plots and visualizations, we first need to import the matplotlib library, which is actually the most popular Python library for creating plots and visualizations. And actually as convention, we import matplotlib.pyplot as PLT. So PLT is actually the most commonly used abbreviation here, so let's do this. And now we want to plot the numerical columns in our Titanic data frame. So we have some numerical columns here. We have the survived column, the P-class column, the H column, zipsp, parch, and also the fair column. And we can do this by simply calling here the plot method on our Titanic data frame. So for Pandas data frames and Pandas series, there is the built-in method .plot. And before we run the cell here, we have to also call the show method. So this is a direct matplotlib.pyplot method. And with the show method, we can actually display our graph or our plot. So always when we create one or several plots with matplotlib, as a very last argument, we have to call here the show method. So let's simply call here the plot method on our entire Titanic data frame, and let's run the cell here. And here we can see that we actually see nothing. So by default, the plot method creates here a line plot with on the x-axis the index. So here we have the range index from 0 till 891. So these are actually the passenger numbers. And on the y-axis, we have actually the specific values in our numerical columns. And for each column, we have actually here a line plot. So we have 6 columns here, and as we have here 6 line plots within one graph or within one plot, it's quite hard to see anything. And therefore, let's go here inside the brackets with Shift-Tab. And here we can see we have a parameter subplots. And by default, it's set to false, but we can set this also to true here. And by doing so, we are creating for each column a separate subplot. And still it's hard to see anything because the plot size is very small. And there's an additional parameter here. And it's called fix size. And here we can determine the width and the height of the graph. So let's do this here. We have here fix size. And then we have to pass within a tuple the desired width and height of the graph. So for example, we want to have a width of 12 and a height of 8. Then we get here a larger plot. And maybe we should further increase the size here to maybe 15 and 12. So now it's much easier to see and analyze it. So for each column we have here a separate subplot. So here for the survived column, the p-class column, the age column, the zipsp column, parch column, and fair column. And by default all subplots share actually here the x-axis. So we have here at the very bottom one x-axis with the range index from 0 to 891. But we can also create a separate x-axis for each subplot, and there is one parameter here. And the parameter here is share x. So let's have a look here. And by default it's set to true actually, so all subplots share one x-axis. But we can also set this to false, so let's do this. So we have here the share x parameter and we can set it to false. And now we can see here at the bottom of each subplot the x-axis with the range index from 0 till 891. And we can see here on the left-hand side for each subplot actually the y-axis. And here we have a specific y-axis for each subplot. So for example here for the survived column we have values between 0 and 1. So you can see here it's oscillating between 0 and 1. Then here for the p-class column we have the values 1, 2 and 3. Then for the age column we have values between 0 and 80. And a line plot like this is actually good to see the distribution of values. So the majority of ages are here between 20 and 40, but we have some outliers here around 0 and some outliers here around 75, 80. And specifically when we have time series data with a date-time index, so here we have then on the x-axis a date-time index. So for example, starting from the year 2010 until 2015. And specifically in this case, a line plot is very intuitive to see the evolution of some factors over time. So for example, stock prices or weather data. But also here with non-time series data, a line plot makes definitely sense. And here in the zipsp column, we can see that the majority of values are here actually 1. So most of the passengers have one sibling or spouse on board. And also here for the parents and children, the most frequent values are here between 0 and 2. And also here in the fare column, we can see that the most frequent fares are actually quite low here, between 0 and 20. However, there are some outliers here, so we have here some outliers until $400 or $500. And as we have seen on the left-hand side, so for each subplot, we have a different scale for the y-axis, but we can also change this here. So there's the parameter share y. So here we have share y. And by default it's set to false, so for each subplot we have a specific and appropriate y-axis, but we can also set this to true. And here we have for each subplot actually the same y-axis with the same scale. And as we have here the largest scale at the fare column, so the shared y-axis is actually most appropriate here for the fare column. So here we have values between 0 and 500. However, for the parch column, a scale between 0 and 500 does not really make sense. So here we actually see nothing. And therefore, in this case, it definitely makes sense to set the share y parameter to false. And actually, if we are only interested in the h column, and if we only want to visualize the h column, we can also apply the plot method only on the h column. So let's do this. Let's copy here the code. And instead of using here the plot method on the entire Titanic data frame, we use it only on the h column. And if we only use it on the h column, we do not have to define here subplots. So this is not necessary. And maybe we make the figure size a bit smaller here, because we have only one subplot. And also we do not need the parameters share x and share y. So let's plot here the graph. And here we have actually a line plot only for the h column. So we can see here the x-axis with the index labels from 0 to 890. And we can see on the y-axis values between 0 and 80. And the majority of values are here between 20 and 40. And we have some very young passengers that are only a bit older than 0 years old, so babies. And we have some quite old passengers above 70 and until 80. Alright, this was the first video on data visualization, and in the next video we learn how to customize our plot here. So hope to see you there. Bye. Welcome to the Pandas group by section. So group by operations are one of the most powerful data analysis tools in Pandas, and the functionality and flexibility is almost unlimited. And that's why group by is actually my favorite Pandas tool. So it's simply fun to perform group by operations. Alright, so now I want to give you a very first intuition what we can do with the group by method. And let's assume we have here our data frame with male passengers and female passengers. And what we can simply do, we can calculate the mean or the average age over all passengers with the mean method. But what if we are interested in the group-specific mean ages? So for example, the mean age over all female passengers and the mean age of all male passengers. And group by actually provides us the easiest and most comfortable way to do this and to perform group-specific operations. So actually within one line of code we can transform here our data frame into a summary data frame where we have the mean age for all female passengers and the mean age for all male passengers. And we can simply do this with the group by method, where we have to pass the key by which we want to split our data frame here by the sex key. So we have male and female in our sex column, and then we apply the mean method. And by doing so within one line of code, we are getting here our new data frame. So no worry, I will explain this in more detail in the next videos, and we will also practice this in more detail. So this was just a little outlook, and actually this is just the top of the iceberg of what we can do with group by. And as I said, the functionality and complexity is unlimited here. So we will see this in the next videos where we will dive deep into this topic. So I hope to see you there. Bye. Welcome to our first coding video on group by operations. In this and the next video we want to figure out and really understand what group by does in the background. And we also want to understand what a group by object is. So first of all we will have a deeper look into the split part of split, apply and combine. But first of all let's import pandas. And we are working with the Titanic dataset. And let's have a look here at the first 5 rows and the last 5 rows. And also at some meta information with the info method. And for the time being we want to work with a toy example. So we slice our Titanic data frame only for the first 10 rows. And for the columns sex and age. And we are saving here the slice in the variable Titanic slice. So let's do this. And let's have a look here at our slice. So here we have the first 10 passengers and the column sex and age. And now we want to use the group by method on our slice here. And what we actually want to do, we want to split here our data frame by the sex column. So the key is the sex column. And by doing so, we expect that we split here our data frame and then we get all rows or all passengers who are female and we get all rows and passengers who are male. So let's also press here Shift Tab within the brackets. And the most important parameter is here the by parameter, where we have to define the keys by which we want to slice our data frame. And here we have to pass one or several columns, and in this case here, we are passing the sex column. So let's do this here. And here we can see that we get something like a group by object. So let's store here the group by object in the variable GBO, group by object. And let's also check the data type of GBO. So here it's a data frame group by object. And same as with all data types or classes in Python, also the group by object has specific attributes and methods. And one attribute is the groups attribute. So let's try this out here. And here we can see that we have 2 groups in our group by object. So we have the group female with actually all rows where we have a female. So we have in the rows 1, 2, 3, 8, 9 females. So let's check this out here in our data frame. 1, 2, 3, 8 and 9. So here we have actually the index labels where we have females in our data frame. And the second group is the male group. And also here we have the index labels for the rows where we have males. So we have here 0, 4, 5, 6, 7, 0, 4, 5, 6, 7. And now we could also transform here our group by object into a list by using here the list function, and we save our list in the variable L. And let's have a look here at L. So it's actually at a first glance hard to see what we have here, but apparently our list has 2 elements. So the first element starts here with the bracket and ends here, and the second element starts and ends here. So let's check first of all the length of our list, so the amount of elements. So we have 2 elements. And now let's select the first element of our list. So here we have the first element. And here it looks like a tuple. So we have here 2 brackets. And apparently our tuple consists of 2 elements. So we have here the string female. And it seems like that we have here a data frame with all rows where we have a female. And we can also check here the data type. So it should be a tuple. And now we can also select the first element in our tuple, so it should be here female. So let's try this out. And it's a female. And this is apparently a string object. And let's also select the second element of our tuple here. So this looks like a data frame. And indeed here we have a data frame with all rows where we have females. And still here on the left side, the index labels are the same as here in our original data frame. So here we have for the females the index labels 1, 2, 3, 8 and 9. And also here we have 1, 2, 3, 8 and 9. And we can also check here the data types. So this should be a pandas data frame. Exactly. And for the sake of completeness, we can also check the second element in our tuple here. So this time we have here a tuple with the first element the string male and the second element our data frame with rows where we have male passengers. Alright. So what the group by method actually did, it splitted our original data frame into two data frames. And the first data frame contains all rows with female passengers, and the second data frame contains all rows with male passengers. And alternatively, we could also slice our data frame with the log operator and slice for all rows where the sex column is female. So we can also do this in this way here. And here we can see that we get here the same slice. So here we have all rows with females and here we have all rows with females. And we can also save here the slice with all females in the variable Titanic slice female. And we can do the same with male. And then we can check with the equals method whether the data frame with all female passengers, which we created here with the log operator, is actually the same as our sliced group by object here. So here we get a true. So this confirms that the group by method splits our data frame by the key sex and creates two data frames, one female data frame and one male data frame. And we can also iterate over our group by object with a for loop. And for each element in our group by object we want to print the data frame, so we can also do this here. And we get here our female data frame and our male data frame. Alright, so now let's go also back to our slides here. And this is actually exactly what we did right now. So we created here a group by object, and this is actually the split part. So we had here our original data frame, or actually our slice of our data frame with 9 passengers and the sex and age column. And then we applied here the group by method by the key sex. And by doing so we splitted our data frame into two data frames, where in the first data frame we have all female rows here. And in the second data frame we have here all rows where we have a male passenger. So and this is now our group by object. So we have two groups or two data frames split by the key sex. Alright, so we are finished now with this video, and in the next video we can see that we can also split a data frame by more than one key, so by many keys, by 2, 3 or 4 keys. So hope to see you there. Bye! In this video we will split our data frame by more than one key. So in principle we can split our data frames by 1, 2, 3 or whatever number of keys. So this is no problem. And first of all we import pandas as always. And then now we are working with the Summer Olympics data frame, and we will have a look at the first 5 rows here and also add some meta information. And this time we are working with the whole data frame. So no toy examples this time, and let's have a look here at the country column. So now let's first have a look how many different or unique countries we have in our data frame. So up to now athletes from 147 countries have already won medals in some Olympic Games. And in the last video, where we have split our Titanic data frame into a male data frame and a female data frame, we have seen that we can also do this with the log operator and create a group by group. So this is quite easy if we only have 2 groups, so males and females. But if we have here 147 groups, like in this case, then doing this manually with the log operator is getting quite messy, and with the group by method we can do this actually in one line. So let's do this. We are splitting our Summer Olympics data frame by the key country, and we save our group by object in the variable split1. And let's transform our group by object into a list and store it in the variable L. So let's have a look here at our list L. First of all, let's check here the length. So we have 147 countries and the length of our list is 147. And for each country actually we have here in our list a tuple consisting of the country code here starting with Afghanistan. And then the second element here in the tuple is actually the data frame with all rows where we have athletes from Afghanistan. So in total here we have 2 medals, both medals awarded here in Taekwondo. And here we have the second element of our list. It's the country AHO, so actually I do not know which country it is. And then the third element is here Algeria. So we can also randomly select here a data frame. And we slice for the tuple at index position 100 and we slice for the data frame. So let's see what we get here. And we get here a data frame with all medals won by athletes from the Philippines. And now instead of splitting our data frame only by the country, we want to split our data frame by country and gender. So here with our group by method, we have the parameter by, and before we just passed here one column name, but we can pass here a list of multiple column names. So here we are passing the column name country and gender, and by doing so we can split our data frame by country and gender. So let's do this, and we save our group by object in the variable split2. So let's run here the cell. And then we are transforming our group by object into a list and save the list in the variable L2, and let's print here L2. And first of all we can see here the first element. We have here all men from Afghanistan that already won a medal in some Olympic Games. And we can also check here the length of our list too. So intuitively we could say, okay, we have 147 countries and we have male and female, so the number of possible combinations should be 2 times 147. It's 294. So potentially we have 294 groups, but I do think, at least for the small countries, that we have countries where only male athletes or female athletes have already won medals. So I do not expect to have here in our L2 list a length of 294. So let's check this out. And we have only 236 groups. And let's randomly select the group at index position 104. And here we can see that we have the group with female athletes from Ireland. So actually we have here 1, 2, 3, 4, 5, 6 medals that has been awarded to female athletes from Ireland. And apparently here we have a tuple, so we can also check here for the first element in our tuple. And here it's not a string but also a tuple consisting of 2 strings, so here are our 2 groups, so we have Ireland and women. And we can also slice here our tuple for the second element, so the second element here is the data frame. And here we have the data frame with all rows or all medals where we have female athletes from Ireland. And still here on the left side we have here the index labels from our original data frame. Alright, so now in this video we splitted our Summer Olympics data frame not only by 1 key but by 2 keys. And we could also do the same for more keys. So for example, we could say that we want to split our data frame by country, athlete, and let's say the year or the edition of the Olympic Games. Then here Michelle Marie Smith would actually form one group, so female athletes from Ireland who won in the edition 1996 a medal. And a second group would be female athletes also from Ireland that won in the year or in the edition 2000 a medal. So here in this data frame we only would have Sonia O'Sullivan. Alright, we are finished now with this video, and I do think we have now a good impression how group by splits our original data frame in many data frames or in many groups. And in the next video we will learn how split apply combine works. So this is the real power of group by, and I hope to see you in the next video. Bye. In this video we learn how to perform split, apply, combine operations on a data frame with the group by method. So in the last videos we already learned how to split a data frame into groups. And now we apply a function to our group by object, and by doing so we are creating a new combined data frame. This sounds complicated, but you will see that it's really easy and straightforward. So let's start coding, and we import pandas. And we are working with the Titanic dataset. And also this time we are working with our toy example, so we are slicing our Titanic data frame, and we only use in the first 10 rows and the columns sex and age. So here's our toy example. And we have already learned that by applying the group by method and, for example, using the key sex, we are splitting our data frame here into, in this example, 2 data frames. So we have one data frame with all rows where the passenger is female, and we have another data frame with rows where the passenger is male. And we can transform our group by object into a list, and then we can slice our list. And here our first data frame and our group by object is the female data frame, and the second data frame is the male data frame. And now let's assume that we want to calculate the average age of the females and the average age of the male passengers. And therefore we are using here the group by method on our slice. And we group by the sex column, so male and female. And by doing so we are creating a group by object. And then we have to apply a function on our group by object. And the function will be applied on both data frames in our group by object. And after we have applied both functions here, both data frames will be combined to one new data frame. So this sounds complicated, but let's just do it. And we are using the function mean. And let's run the cell and let's see what we get here. So we are getting here a brand new data frame where we have as index here our sex column, so female and male. And we have here a single column, age. And here we have the mean or the average age for all females and for all males. So actually here 28 is the mean or the average of all of the females here in our split. And also here for our males, so 28.25 is the mean or the average of all male passengers here. And by default pandas is just ignoring here the missing value or NaN value. And this is actually all. So with the group by method, we split our original data frame in a female and a male data frame. And then for the female and the male data frame, we calculated the average age, and then we combined the average age of females and the average age of males into one final data frame here. And let's also have a look at our slides here. So here we had our original data frame. Then we used here the group by method and used as a key the sex column. And by doing so we created a group by object. So we split our data frame into all rows where we have females and all rows where we have males. And then we applied the function mean. And by doing so pandas actually calculated the mean age of all females and the mean age of all males. And then both mean values were combined into a brand new data frame. So by applying the group by method, we splitted our data frame, and by using here the mean function, we applied a function on both data frames, and at the same time we combined our groups into a new data frame. Alright, so now let's go back coding. And in theory, as a function here, we can apply any function. And the most frequently used functions are actually aggregations, so taking the mean or the sum or the min or the max of the groups. So as a next step, we could also use here the sum function on our group by object. So let's see what we get here. And we are using here the group by and sum function on our whole data frame. So we are having all 891 rows and all columns, and let's see what we get here. So again we splitted our data frame here by the sex column, so we have female and male. And then we have for each column here actually the sum. So we have here the survived column, and in total 233 female passengers survived and only 109 male passengers survived. And we have also the sum of the P class, so in this case it doesn't make really sense. And we have also the sum of the age, so all females together are 7,286 years old. And we have also the sum of all siblings and spouses. So all female passengers together had 218 siblings and spouses on board. And we have the same here for parents and children. And also we have the sum of the fare. So all females together paid about $14,000 or pound. And all male passengers together paid slightly more than the females. And you can see here that taking the sum does not make sense for all columns. So let's assume we are only interested in the survived column, and we can do so here by here just only choosing the survived column, so dot survived. So this is actually method chaining. So first of all, we are using the group by method on our Titanic data frame. And we group our Titanic data frame by the sex column. Then we are only interested in the survived column. And for each group, so female and male, we want to know the amount of female and male who survived. Alright, so let's do this. And we can see here that we only get aggregations for the survived columns. So we have 233 females who survived and only 109 men. Alright, and of course we can select more than one column. So here we only selected the survived column, but we can also select the fare and the age column. So we have to pass here within our spare brackets a list with the fare and the age column. And we split our data frame by the sex column, and then we want to know the maximum. So we want to know the maximum fare paid by a female and by a male, and we want to know the maximum age of females and males. So let's do this here. So the highest fare paid by a female is 512, and also the highest fare paid by a male is also 512. And the oldest female on board was 63 years old, and the oldest male on board was 80 years old. Alright, so now let's again split our whole Titanic data frame by the sex column. And we want to calculate the mean on all columns. So let's do this, and we assign the variable new data frame. So let's have a look at new data frame. So here we have the mean for all columns by female and male. So on average 74% of all females survived the Titanic disaster and only about 19% of all males. And the average passenger class is a little bit higher for the males. And also the male passengers are a bit older on average than the female passengers. And on average the female passengers paid more for their tickets than the male passengers. So on average the females paid $44 or pound and the males paid $25 or pound. Alright, and now we can also visualize here our new data frame, and we import matplotlib and we use the Seaborn style. And we want to have a bar plot for each column where we can see the difference between female and male. So let's do this and let's have a look here. So here we use the subplots true. So for each column here we have a subplot, and here the first subplot is for survive. And we can see here on the left side are the females and on the right side are the males. And we can see that the survival rate is tremendously higher for females. And here we have the average of the passenger class, and here the average of the age. So here we can see that on average the male passengers were a bit older than the female passengers. And here we have the information about the fare. So on average the female passengers paid significantly more than the male passengers. Alright, so now we are finished with our video, and in the next video we will apply our new split apply combine skills to some more cases. So hope to see you there. Bye! In this video we will code some more examples of split apply combine, and by doing so we want to get more insight into our data and we want to find more interesting facts and relationships. Alright, so now let's first of all import Pandas, and now we are working with the Summer Olympics dataset. And now we want to find the 20 most successful countries in the history of Summer Olympic Games with the highest number of medals. And therefore we have to split here our summer data frame by the column or by the key country. And by doing so we are getting about 140 different groups or countries. And for each group we want to count the amount of medals that were already awarded to athletes from the country. And therefore we are only interested in the medal column. And for each group we want to count the amount of non-null values in the medal column, and we can do this with the count method. And we are storing the results in the variable medals per country, so let's do this, and also print medals per country. And we can see here on the left side we have the country, and on the right side the total amount of medals that were awarded to athletes from the respective country. So for example, Afghanistan has 2 medals, then here Belgium has 411 medals, and Brazil has 431 medals, and so on. And what we actually wanted to know is actually the 20 most successful countries. So what we can do now, actually we can chain here the method n-largest, and we want to have the 20 countries with the most medals, so let's pass here n equals 20. And by running the cell we are actually overriding here our variables, so let's do this. And here we have the 20 most successful countries. So no surprise that the most successful country is USA. And the second most successful country, I think this is the former Soviet Union, and then we have Great Britain, France, Germany, Italy, Australia, Hungary, Sweden, Netherlands, and so on. So actually on rank 20 is Denmark with 507 medals. And we can also plot our results here in a bar chart. So let's first of all import matplotlib as always, and we use the Seaborn style. And then we are plotting here our Pandas series medals per country, and we are using a bar chart, and the figure size is 14:8, and we are using a font size of 14, and we have the X label of country, the Y label number of medals, and the title is Summer Olympic Games total medals per country. So let's see what we get here. And here we have the bar chart of the 20 most successful countries in the Summer Olympic Games. So number 1 is here USA with over 4,000 medals. Then we have the former Soviet Union, Great Britain, France, until Poland and Denmark. Alright, so now let's head over to our Titanic dataset. And we can use here the describe method to get some more summary statistics on our numerical columns. So here we can see, for example, that the average fare that all passengers paid was 32. And we can also apply the mean method directly on the fare column. So also here we should get 32.2. And this is actually the average fare for all passengers. But now let's assume that we want to know the average fare for all passenger classes. And we can do this by splitting our data frame into the passenger classes. So we have 3 passenger classes. Then we only select the fare column. And we want to know the average or the mean fare paid by the 3 passenger classes. So let's do this here. And it's actually no surprise that the average fare for the first class is highest, so 84. Then the average fare paid by second class passengers is 20.6. And third class passengers paid on average 13.6. And we can also take the sum over the whole survived column. So we might recall that in the survived column we have 1 for survived and 0 for not survived. And by taking the sum over the survived column, we should get the total amount of passengers who actually survived the disaster. So let's do this. So in total, 342 passengers survived. And by calculating the mean on the survived column, we are actually calculating the survival rate. So 1 stands for survived, 0 for not survived, and by taking the mean, we are actually getting the survival rate. So only 38.3 of all passengers survived the disaster. And we know that there was a clear code of conduct when filling the lifeboats, so women and children first. And now we can check if they really followed the code of conduct, and we can do so by calculating the survival rate for different groups. So for example, we can calculate the survival rate for women, for men, for children, for adults, and also for passenger classes. And as a first step, let's calculate the survival rate by gender. So the survival rate of all female passengers and all male passengers. And we can see that there is a significant difference. So the total survival rate over all passengers was 38%, but the survival rate for the female passengers were 74%, and for all male passengers only 18 or 19%. And we can also check the survival rate by passenger class. And we can see that first and second class passengers had some priority when it comes to getting a place in a lifeboat. So 63% of all first class passengers survived, and only 24% of all third class passengers survived. So this is a clear difference. And we can also split our data frame into adult and children. However, we do not have a column with adult or children, and therefore we have to create a new column. So we create the column adult children, and first of all we assign the value adult to all rows, and then we filter our data frame, and for all rows where the age is below 18, we override the value in the adult children column by the value child. So let's do this here. And let's have a look at our data frame with our new column adult child. So we can see here for the first 5 passengers, they are all older than 18 years old, and therefore we have here the value adult. But let's have a look at some more rows here. So here the passenger at index position 7 is actually only 2 years old, and here we have the value child in the column adult child. Alright, and let's also now analyze our adult child column by counting the values with the method value counts. So in total we have 778 adults and 113 children. And now we can also split and group our Titanic data frame by the column adult child. And we can calculate the survival rate for adults and for children. So let's do this. So on average 36% of all adults survived, and about 54% of all children survived the disaster. And we have already learned that we can use more than one key, so we can use 2, 3 or even more keys to split our data frame. And now as the code of conduct was women and children first, we want to split our data frame by the sex and by the adult or child column. And by doing so we can split our data frame into 4 groups. And we want to analyze the survived column, but first of all we want to count the number of passengers in each group. So let's do this here with the count method. So here we can see we have 4 different groups. So we have the combination of female and adult, we have the combination female child, and we have the combination male adult and male child. So here we have actually a multi-index or hierarchical index, where the first index column is in the sex column and the second the adult child column. And here on the right side we have the values, so the amount of passengers in each group. So we have here a Pandas series with a hierarchical index. And now we want to calculate the survival rate for all 4 groups. And instead of applying the count method, we now can apply the mean method. And what we can already do, we can sort our 4 groups from the highest survival rate to the lowest survival rate with the sort values method and passing false to the ascending parameter. So we have a descending order starting with the group with the highest survival rate until the group with the lowest survival rate. So let's do this here. And here we can see the group with the highest survival rate is actually female adults with 75% survival rate. Then the second highest survival rate is actually female child with 69%. Then we have male child with 39%. And by far the lowest survival rate had actually adult male passengers with only 16.5%. So again, here we have a Pandas series with an hierarchical index, and we can also store here our Pandas series in the variable women and children first. So this is the same as here above. And now we can also visualize the survival rate of the groups by plotting our Pandas series women and children first, and we are using a bar plot. And we are setting the fixed size to 14.8 and the font size to 14. And let's run here the cell and let's see what we get here. So we have here the bar chart Titanic survival rate by sex age groups. And we can see here on the y-axis we have the survival rate. And the group with the highest survival rate is actually female adult. Then the second highest survival rate is female child. And the by far lowest survival rate has the adult male group here. Alright, we are finished now with this video, and I hope to see you in the next video. Bye! In this video we are going to import our very first time series data, and in our files we have a CSV file called temperature or temp, and it contains temperature information for New York and Los Angeles for the years 2013 till 2016. And in a very first step there's actually no difference between importing non-time series data and time series data from CSV files. So first of all we import pandas. And then we are using the method readCSV. So we are importing our CSV file temperature or temp, and we actually store our new data frame then in the variable temperature. And let's have a very first look here at our data frame. So here we can see the first 5 rows. And actually we have 3 columns. So we have the column datetime, we have LA for Los Angeles, and we have New York. And apparently here as the values of our data frame we have actually the temperature at the specific time in the specific city. And the temperature is here actually in degrees Celsius. So for example here we have in January 11.7 in LA and minus 1.1 degrees Celsius in New York. So let's get some meter information with the info method. And here on the left hand side we have a range index, and we have actually 35,064 rows. So we have over 35,000 different timestamps here. And we have actually 3 columns. So we have the datetime column, and obviously here we have string data type. So here we have object, and this is a clear indication that here we have strings in the column. Then we have the column Los Angeles with float data types. So these are here degrees Celsius values, and therefore float data type makes sense. And also here for the New York column we have also a float data type. So the first problem is here that in the datetime column we actually do not have a specific datetime data type. So we have a string data type, and this might not be really helpful. And therefore in a first step we can try to transform datetime information that is actually stored here in strings into a datetime data type or format. And we can do this immediately when we import the data frame. So the readCSV method provides some parameters that helps to import the datetime information, and let's go here inside. And here we can see that we have the parameter pass dates, and by default it's set to false. but let's have a look here. So parse dates. And here we can actually pass column labels for columns that we want to transform from a string data type to a datetime data type. And we have to do this as a list. And obviously our column that we want to transform is here the datetime column. So we pass here datetime. And we can also have a look at the documentation for the parse dates parameter. So here it is. And for example, here we can pass the Boolean value true, and then Panda tries to parse the index into a datetime format. But obviously here we have a range index, so we do not have any datetime information on the index. Or we can pass a list of integers or names, so we can pass either a list with the index position of the columns or the column labels. And this is exactly what we do here. We pass the column label datetime, and let's see what we get here. So we're actually overriding our variable temperature. And let's have a look here again at the info method. And here we can see now that the data type changed from object to datetime 64. And here in square brackets we have nanoseconds. So the precision is nanoseconds if we want to have this. So now we can also update here the view on the first 5 rows. And now we have here the column datetime with the data type datetime 64. And now we can also slice here for an element in our datetime column, and we can select here the very first element with the ilog operator. And here we have a so-called timestamp. And a timestamp is actually a single point in time. So for example, here we have the year 2013, we have January, and we have January the 1st. And then also we have information on the time, so we have midnight here. So these are the hours, then we have minutes, and then seconds. And as we can see above, our data frame provides hourly temperature information. So the increment is 1 hour, and we are starting here with January the 1st at midnight. Then our next timestamp is still January the 1st, 1 o'clock a.m. Then we have 2 o'clock a.m., 3 o'clock, and so on. And we can also check here the data type of the timestamp with the type method. And this is here a Pandas timestamp. So the timestamp is a specific Pandas data type to store datetime information. And whenever we have datetime information like this, it makes sense to have the datetime as the index of our data frame. And by doing so, this gives us a lot of additional functionality. So we can already do this when we import our data with the readCSV method. And we have already seen that there is the parameter index calls. And here we can pass the column label for the column that we want to have as index, and in this case it's here datetime. So this is actually a very common workflow with time series, that when we import the data, we first of all pass the columns that contain datetime information with the parameter parse dates, and then we set these columns as the index. So let's do this here. And we override our variable temperature. And let's have again a look at the first 5 rows. And now we can see here that we have our datetime column now as the index. And we can also check this with the info method. So we can see here that we have a so-called datetime index. And we have 35,000 entries, and these range from January the 1st, 2013 midnight until December 31st of 2016, 11 o'clock p.m. So we have here hourly temperature information for New York and Los Angeles for the years 2013 till 2016. And we can also call here the index attribute to further analyze our new index. And here we have our datetime index, and here we have all of the timestamps. So a datetime index is actually the collection of many timestamps. And we can see at the bottom that we have the data type datetime 64. And as index label we have datetime, and we have 35,000 entries. And we can also select a single element in our index. So let's select the very first element. And this is here the very first timestamp. So January the 1st, 2013 at midnight. Alright, these were the first steps with time series, and I hope to see you also in the next video. Bye! In the last video we imported our very first time series data, and we converted the column datetime into the datetime index of our data frame. And we did this by passing the column label to the parameters parseDates and indexCol of the readCSV method. And in this video we will have a look at the second, more explicit alternative to do this. And here we need two steps. So first of all we transform the data type of the column to datetime. And we can do this with the direct pandas method to datetime. And the second, we set the column as the index of our data frame with the setIndex method. And then in the second part of this video, we will have a closer look to the toDateTime method, and we learn in more detail how to transform different strings into datetime objects. So let's import pandas here, and we import our temperature CSV file. And here we have the first 5 rows, and we also call here the info method. So here we have now the column datetime, and we have the data type object. So these are all strings here. And we can also explicitly select the datetime column. So let's do this. And here we can see at the end that here we have the data type object. And we can also select here a single element of our Pandas series or column. So here we can see that this is actually a string. And now we can convert the data type of our column to datetime with the direct pandas method to datetime. So here we pass our column datetime. And also here we get a pandas series with all of our dates here. And if we have a look here at the very end, we can see here that we have the data type datetime64. So with the method datetime we can transform strings into datetime objects. And now again we want to have the datetime column here as being the datetime index of our whole data frame. And we can do this in 2 steps. So first of all we convert the data type with the method toDateTime. And by doing so we're getting here actually here the pandas series. And then we pass here the pandas series to the method setIndex. So let's try this out here. So here we can see now on the left hand side that instead of having a range index we have our column datetime, and still we have here the column datetime, so we can drop the column here. And now this looks quite good, and then we can override our variable temperature. So let's do this. And let's again have a look at the first 5 rows. So here we have our new data frame where we have on the left hand side our datetime index, and we have the 2 columns LA and New York. And let's also inspect the info method. So here we can see now our datetime index with over 35,000 entries and our 2 columns. And we can also further inspect our datetime index with the attribute index. So here we have the datetime index with all of the timestamps, and we can also select a single element here. So the first one, and here we have a timestamp. And actually Pandas is quite smart and versatile when it comes to converting strings to datetime objects. So actually Pandas can handle many different formats, and the most standard format is here actually 215-0520. So we have here the 20th of May 2015, and we have here the format year, then we have a minus or dash, then we have months, then again a minus or dash, and then we have the day. And this is no problem to convert into a datetime object. So here we get the timestamp. So here in our string we have the information about the date, but we haven't passed any information on the time. And by default, Pandas assumes actually here midnight. So we have midnight, 0 o'clock actually. So this is here for the hours, the minutes and the seconds. But within our string we can also pass information on the time. So let's do this, for example 10 o'clock. And then we get here 10 o'clock, and we can also provide information on the minutes. So let's assume 10:30. And we can also provide additional information on the seconds. So for example, 20 seconds. And as I said before, actually Pandas and the method toDateTime is quite powerful and versatile because it can actually recognize and convert many different formats. So for example, here we have a different format. So we have between year, month and day, no separator at all, but this still works. And again, here by default, we have here midnight if we do not pass any information on the time. And we can also use different separators. So for example, here slashes. Or we can use white spaces. And there's only one thing that we have to keep in mind here. So by default, the sequence is year, month and day. And for example, if we pass now year, day and month, so our intention here is to get the date 20th of May 2015. But here we switched day and month, and here Pandas gets a problem. So here we get an error message and it says months must be between 1 and 12. So by default, Pandas expects here the sequence year, month and day. And this is definitely a source for errors, but we can also prevent this by having for the month, for example, May. So this also works. And we can also locate May at the very left side of our string or on the right hand side. And actually it doesn't matter if we have here uppercase letters or lowercase letters or whatever, so it works. And instead of having here 20 for the day, we can also have here 20th with the th, so this also works. So to summarize, there's hardly any combination here which does not work. And we can also pass a sequence with dates to the toDateTime method. So for example, here we have a list. And here above we passed a Pandas series, our column datetime. And now we simply pass a list with 2 dates, and this also works here. And whenever we pass more than one date, we get here a datetime index. So here we have now a datetime index with 2 timestamps. And we can also pass a sequence of dates where for at least one element, even Pandas will not be able to convert this into datetime. So for example, elephant. So this might be impossible to convert, but we can try here, and let's have a look what toDateTime does here. And by default, we get here an error message. So unknown string format elephant. So we have seen here above that Pandas can handle many string formats, but of course elephant is quite impossible to convert. And by default we are getting an error message, but we can change this. So let's have a look here. And here we have the parameter errors. And by default it's set to raise. So let's have a look here at the documentation. So if we have the argument raise, then the invalid passing will raise an exception, so we get here an error message. But we can also pass here coerce, and then the invalid passing will be set as NAT. So this stands for not a time. So let's try this out, and let's pass coerce to the parameter errors. And let's run the cell here. And here we can see that we nevertheless get a datetime index with 2 timestamps and actually the element NAT, which stands for not a time. So also here, when having some strings which cannot be converted to datetime, then still the toDateTime method is quite smart and versatile. Alright, with this we are finished now with this video, and I hope to see you also in the next one. Bye! In this video we are going to further inspect our temperature time series, and we still have imported Pandas, and we still have our data frame temperature with the datetime index here on the left hand side and the 2 columns LA and New York. And we can also call here the info method. And we can see here that in the column LA we have obviously 2 missing values. So we have 35,064 timestamps, And for LA, we have only information regarding the temperature for 35,062 timestamps. So there might be 2 missing values. And we can also further analyze our columns with the describe method. So here we can see the amount of non-missing values. Then here we have the mean temperature. So it's no surprise that for LA it's higher than for New York. Then we have the minimum temperature, and for New York it's minus 22 degrees Celsius. And also here we have the maximum temperatures, and so the maximum for LA was higher than for New York with 42.3. And we can also further analyze a single column, so for example the LA column, and we can do this for example with the value counts method. And here we can see the most frequent value, or the most frequent temperature, was 16.2. And actually one of the most powerful tools to analyze time series is graphically with line charts. And therefore we import matplotlib.pyplot as PLT. And by visualizing time series with line charts, we can see how features like temperatures in New York and LA change over time. And we can also compare 2 or many time series graphically. So, and in Pandas we can do this quite simply with the plot method. So here we use the plot method on our data frame temperature, and we use the fixed size 15.7. And here we can actually see in blue the time series for LA, and in orange the time series for New York. And by default, when we are calling the plot method on a data frame, then Pandas creates here a line plot. So here we have a line plot with on the x-axis the index, and here with a datetime index we have here on the x-axis actually our date time, and on the y-axis we have the temperature. So now here we have the graph for New York and LA in one graph, but we can also create subplots, and we can do this here by passing true to the subplots parameter. So here we have now the 2 subplots organized vertically, one above the other, but we can also change this here. And we have actually the parameter layout. So let's try this out here, and let's have a look. And to the parameter layout we can pass a tuple, where on the left hand side we can define the amount of rows, and on the right hand side the amount of columns. So here the default setting is that we have 2 rows and 1 column. But if you want to organize here our 2 subplots horizontally side by side, we can also change this here. So we can say that we want to have 1 row and 2 columns. And here we are. So here we have organized the 2 subplots side by side. And still it's quite hard to compare the 2 time series, because here the scale on the y-axis is different. So here in New York we are starting with the minus 20 degrees, and here for LA with about 0. And we've already learned that there's an additional parameter called share y. So let's do this here. And here we can define whether the 2 subplots should share the same y-axis. And in this case, we want to compare both time series. So actually they should have the same y-axis, and therefore we can set here the share y parameter to true. And now actually we have here the same y-axis for both subplots. And here we can see that in summertime there's no huge difference between New York and LA. So here we are about 30 degrees. However, there's a huge difference here in wintertime. So in wintertime in New York we have until minus 10 or minus 20 degrees. And here in LA we hardly get temperatures under 0 degrees here. And still we can see here that these are not optimal graphs, because here we have so many data points, because we have hourly data. And it might make more sense to have here, for example, weekly or monthly data. So for visualizing our time series, it might be better to transform to weekly or monthly. And in the next videos, we will also learn how to aggregate time series to, let's say, weekly or monthly data. But for the time being, we are now finished with this video, and I hope to see you in the next one. Bye! In this video, we learn how to index or slice time series for particular timestamps or time periods. So, for example, we can only select the temperature information for the year 2015 or for the month May to 14, and we can simply do this with the log operator. But first of all, let's import pandas. And for indexing and slicing time series, we need to have a datetime index in our data frame. And this is exactly what we are doing here. So we are importing our CSV file temperature, and we are passing the column datetime to the parameters pass dates and index columns. So now here we have on the left-hand side our datetime index, and we can also confirm this with the info method. So here we have the datetime index. And same with all other indexes. We can select and slice for index labels by using the log operator. So with the log operator, we can perform label-based indexing. And here with a datetime index, our labels are actually here datetimes. And let's assume that we only want to select one timestamp. So for example here, the 1st of January to 13 at 1 o'clock AM. And we can simply do this by passing the timestamp as a string here to the log operator. And here we can see the temperature information for the specific timestamp here. So we have here 1 o'clock. And in LA we have 10.7 degrees, and in New York minus 1.7, so here. So here we passed an entire timestamp with information on the date and also on the time, so 1 o'clock. But we can also pass only to 15, and by doing so we are selecting all rows or all timestamps in the year 2015. So let's try this out here. And here we can see that here we have timestamps to 15 starting from the very first timestamp at January the 1st at midnight. And so we have here all timestamps into 15 with hourly increments. And the very last row we have here the 31st of December to 15 at 11 o'clock PM. So these are all timestamps in the year 2015, and in total we have 8,760 rows or timestamps. And we can also slice for particular months. So for example here for May to 15. And here we are getting all timestamps in May to 15, starting from the 1st of May midnight until the 31st 11 o'clock in the evening. And in total we have here 744 rows or timestamps. And of course we can also select a single day. So for example here the 20th of May 2015. And I think we should get here 24 rows. So we have hourly data and 1 day. So let's check here the shape. And here we have 24 rows, so for each hour on the 20th of May 2015. And we can also add here time data, so for example 10 o'clock for the 20th of May. And this also works, so here this is one single timestamp. And in theory we can also add information on the minutes and seconds here, so for example here we have 10:30. But here we get an error message because we have only hourly data. So there is no timestamp 10:30. Alright. And we can also index or slice for time periods. So for example, from January the 1st to 15 until the very last day to 15. So let's try this out here. So we are starting here at midnight on January the 1st. And the last timestamp is at 11 o'clock at the 31st. And actually slicing from the 1st of January until the 31st of December is actually identical to slicing only for the year 2015. So here we can check this with the equals method. And we should get here a true. However, of course, here with the slicing notation, we can be more versatile. So, for example, we can also slice from the 15th of April to 15 till the 23rd of February to 16. So obviously in this case, we cannot only pass here to 15 or to 16. And we can also slice from the 20th of May to 15 until the very last timestamp. So here we are starting with the 20th of May, and the very last timestamp is here the very last timestamp in our data frame. So the 31st of December to 16, 11 o'clock p.m. And we can also slice our data frame from the beginning until, for example, the 20th of May to 15. So here we are starting into 13 until the 20th of May to 15, 11 o'clock. And same as with the toDateTime method, Pandas can handle here all kinds of formats. So for example, here we can select for the 20th of February to 15, and we can do this in different formats here. For example, in this format, and this still works here. So starting from midnight till 11 o'clock p.m. However, there's one thing that we cannot do. So let's assume that we want to select several single timestamps. So for example here, the 20th of May to 15, 10 o'clock, and the 20th of May to 15, 12 o'clock. And this does not work here. And in this case, first of all, we have to transform the two timestamps into a datetime index. And we can do this with the method pd.toDateTime. So we are passing here a list of the two timestamps, and let's see what we get here. And we're getting here actually the datetime index with our two timestamps. And now we can index our data frame with the log operator by passing here the datetime index. And by doing so, we are getting here the two timestamps, so 10 o'clock and 12 o'clock, and the information for Los Angeles and New York. Alright, this was the video on indexing and slicing time series. And with a datetime index and the log operator, this is actually quite easy and versatile. And with this, we are finished here, and I hope to see you also in the next video. Bye!